In the vastness of space, there's a shadow, an unbreakable barrier humanity has long tried to understand. It's not just a number, it's the ultimate speed limit, the edge of the impossible. Imagine chasing lightning's flash, or reaching for a star's glow, only to realise, no matter how fast you run, you can never catch it. This isn't just physics, it's the very fabric of reality. About a century ago, scientists uncovered a truth so profound, it shattered old ideas and rewrote our universe. So Richard Feynman, one of the greatest minds, revealed something that will melt your mind, a secret that ties everything together, yet keeps us forever out of reach. Because at the end of all our pursuits, there's a cosmic speed limit, the final boundary we'll never cross. And understanding it might change everything. The speed of light isn't just some random number in a cosmic scoreboard. It's the very fabric that ties our universe together, a fundamental pillar upon which modern physics stands. When physicists talk about the speed of light, approximately 299,792 kilometers per second, or about 186,282 miles per second, they're referring to a universal constant often denoted by c. But what makes this constant so profound isn't just its value, it's the deep, almost paradoxical role it plays in the structure of reality itself. Imagine trying to chase down a flash of lightning or catch the glow of a distant star. No matter how fast you run, or how powerful your telescope is, you'll never see light travelling slower or faster than this fixed speed. That universality is mind-boggling. It's the cosmic speed limit, a boundary that no object with mass can reach or surpass. As an object accelerates closer to light speed, its energy needs skyrocket toward infinity, like trying to fill a bucket with a hole that gets bigger the faster you pour water in. No matter the effort, you'll never overfill it. That's why, in our universe, nothing with mass can ever attain or exceed light speed. This limit isn't just about preventing objects from zipping through space faster than light. It's woven into the very core of how reality operates. Einstein's special relativity revealed that space and time are intertwined in a fabric called spacetime. The speed of light emerges as the maximum rate at which information and causality can propagate through this fabric. Nothing can carry a signal faster than light, ensuring the cause and effect chain remains intact. As we prepare to journey millions of light years away to witness this cosmic marvel, let's ground ourselves for a moment. I'm fascinated by the idea of us all watching this from our tiny corner of the universe. Let me know in the comments what time it is where you are and whether you're watching this under sunlight or starlight. And if you're ready for the voyage, hitting that like button and subscribing tells me you're on board. Without this speed limit, effects could occur before their causes, a scenario that defies logic and physics. Understanding why light speed is the ceiling unlocks a trove of surprising phenomena. Take time dilation. When you approach the speed of light, time for you slows down relative to a stationary observer. This isn't just science fiction, it's been experimentally confirmed. Particles travelling near light speed live longer than expected, a phenomenon crucial for technologies like GPS, where tiny time differences matter for accuracy. Without the influence of the speed of light on time, navigation systems would be hopelessly flawed. Length contraction is another key effect. Objects moving close to light speed appear shortened along their direction of motion to a stationary observer. It's as if the universe itself shrivels objects to prevent any attempt to reach or breach this cosmic limit. This contraction isn't just a quirky side effect. It's a fundamental aspect of relativity, demonstrating how deeply the speed of light is ingrained in space-time structure. The speed of light also acts as a boundary for energy and mass conversion. According to relativity, as you accelerate mass toward light speed, its relativistic mass increases, demanding more energy. To reach light speed, an infinite amount of energy would be required, a physical impossibility. This explains why particles with rest mass, like humans and spacecraft, are forever bound by this speed barrier. Only massless particles, like photons, travel at this universal limit, mediating electromagnetic forces throughout the universe. In essence, the speed of light isn't just a number, it's the heartbeat of reality's rhythm. It defines the structure of spacetime, sets the ultimate boundary for motion and information transfer, and shapes the very nature of how the universe operates. Without this speed limit, the universe would unravel into chaos. It's a cosmic safeguard etched into the laws governing everything from the tiniest particles to entire galaxies. Understanding and accepting this limit is what makes the universe so intriguingly stable, yet endlessly fascinating. It reveals that reality is much stranger and more wondrous than our daily experience suggests, just waiting for us to peel back the layers and uncover what lies beneath. Einstein's theory of relativity didn't just tweak the old ideas about space and time, it turned everything upside down. Before Einstein, the prevailing belief was rooted in Newtonian physics. Space and time were absolute, unchanging frameworks. Space was like a fixed stage where events unfolded and time ticked away uniformly for everyone everywhere. But Einstein, with his mind-bending insights, showed that isn't how the universe works at all. The special theory of relativity, which Einstein unveiled in 1905, introduced a radical concept. The laws of physics are the same for all observers in uniform motion, and the speed of light in a vacuum is constant no matter what. This meant that if you're moving close to the speed of light, your experience of space and time would be drastically different from someone standing still. Measurements of time and distance depend on your frame of reference. Clocks moving at high speeds tick slower compared to stationary clocks. This effect, known as time dilation, had profound implications. Time itself isn't an absolute ticking clock, but a flexible dimension woven into the fabric of the universe. What's truly mind-blowing is how special relativity blurred the line between space and time. Einstein unified them into a single four-dimensional fabric called spacetime. Picture space and time not as separate entities, but as two sides of the same coin. When objects move, their position in space and their position in time are intertwined. Changing your velocity alters how you perceive both, connecting them in ways that defy intuition. Then came general relativity in 1915, deepening this rethinking by revealing that gravity isn't a force acting at a distance, as Newton thought, but a curvature of space-time itself. Massive objects like stars and planets warp the fabric of space-time beneath them. This warping dictates how objects move, which we interpret as gravity. If you think of space-time as a stretched rubber sheet, placing a heavy ball in the middle causes it to dip. Smaller balls rolled near the dip will spiral inward. This is how the universe's gravitational dance works, a graceful curving rather than a pulling force. General relativity explained phenomena that had puzzled scientists for centuries. It predicted phenomena like the bending of light around massive objects, gravitational lensing, that was later observed during solar eclipses. It also forecasted the existence of black holes, regions where space-time becomes warped so severely that nothing, not even light, can escape. The big shift? Space and time are dynamic, malleable constructs responsive to matter and energy. Instead of static backgrounds, they become participants in the universe's story. Gravity is not a force pulling objects together, it's the geometry of space-time shaping the paths particles and light follow. This worldview revolutionized physics, giving us a universe in which the very fabric of reality is flexible and curved. Einstein's insights didn't just change the equations, they rewired our understanding of the cosmos. Space and time are stranger and more beautiful than anyone had ever imagined. Intertwined, relative, warped. They are the stage and the actors in a cosmic ballet where the choreography is written by the curvature of spacetime itself. And here's the mind-blower. The very notions of absolute space and absolute time, long considered the bedrock of physics, are illusions. The universe isn't steady and fixed, it's fluid, dynamic, and surprisingly elastic. Let's explore the core principles of special relativity, the theory that revolutionized our understanding of space and time. It is based on two fundamental ideas that challenge intuition, but have been confirmed through experiments. The first is the principle of relativity. Imagine floating inside a frictionless spaceship moving at constant velocity through space. If you perform experiments, like measuring the speed of a tossed ball, results will be identical to those on Earth. No experiment inside can reveal whether you're moving or at rest. The laws of physics are the same for all observers in uniform motion. This idea, that no preferred frame of reference exists, is revolutionary. Before Einstein, Many believed in an absolute rest frame, a universal backdrop of fixed space. Einstein argued that all motion is relative. If you're moving steadily, everything behaves as if you're stationary. The concept of absolute rest or motion is discarded unless compared to something external. The second principle is the constancy of the speed of light. Einstein proposed that the speed of light in vacuum, about 299,792,458 meters per second, is always the same, regardless of the observer's motion or the light source's approach or recession. This defies everyday experience where speeds combine depending on relative motion. For example, throwing a ball from a moving car. But light always travels at the same speed for all observers, whether stationary, moving toward, or away from it. If you're stationary, moving toward or away from a light beam, you'll measure the same speed. This was a radical departure from classical physics, requiring space and time to adapt for invariance. From these principles, relativity of motion and invariant light speed, arise astonishing consequences. Since light speed is a universal limit, nothing with mass can reach it. Equations show that as objects accelerate closer to light speed, their effective mass increases, not just classical mass, but an energy-related increase reflecting the effort needed to accelerate further. To reach light speed, an infinite amount of energy would be required, which is impossible. The nature of time also changes. Clocks in different inertial frames run at different rates, a phenomenon called time dilation. A twin travelling near light speed on a spaceship would return younger than their sibling who stayed on Earth. Space and time are intertwined into a fabric called spacetime, which contracts and stretches depending on your motion. Moving faster affects both spatial and temporal measurements, intertwining space and time into a single, observer-dependent fabric. The concept of simultaneity, that whether two events happen at the same time, depends on the observer's frame of reference. Two observers moving relative to each other will disagree on whether two lightning strikes occurred simultaneously. This impacts how cause and effect are perceived. The relativity of simultaneity demonstrates that observations depend on the observer's frame. There is no absolute now. All these principles, relativity, constant light speed, and the space-time connection, challenge intuitive notions. They reveal that the universe is a dynamic, flexible fabric, woven by the laws of physics, not a static stage for independent events. These ideas turn our understanding upside down and show a universe more strange than everyday experience suggests. Feynman described this universe as a tapestry, explaining how our basic assumptions are challenged. Understanding these principles is fundamental, underpinning much of modern physics, including quantum mechanics and cosmology. They explain phenomena and expand comprehension, showing a universe that is intricate, interconnected, and surprising. This framework explains limitations on faster-than-light travel, the relativity of motion, and simultaneity. It reorganizes space and time, replacing the idea of an absolute universe with one that is observer-dependent and interconnected. The interconnectedness means what seems universal depends on the observer's frame. Ultimately, special relativity reveals that, at fundamental levels, the universe is a malleable, interconnected structure, an elegant yet complex fabric governed by speed limits and relative observations. It paved the way for ideas like general relativity and continues to influence our understanding of the cosmos. These principles are profound insights about existence, emphasizing that the universe is stranger and more fascinating than common sense suggests. They show that physics is less about static objects and more about dynamic relationships, an ongoing quest to understand the universe's true nature. Imagine trying to push a shopping cart filled with bricks faster and faster. The harder you push, the heavier it feels, right? Now, replace the shopping cart with any object with mass, be it a spaceship, a ball, or a tiny particle. As that object accelerates toward the speed of light, it experiences a similar kind of weight increase, but on a cosmic scale. Here's what really makes the speed of light an unbreakable barrier. Every object with mass has a property called rest mass. It's mass when not moving relative to you. As it accelerates, kinetic energy, the energy of motion, increases. To make an object go faster, you need to give it more energy. But as it nears the speed of light, the energy required to increase its speed even slightly doesn't just increase, it skyrockets. Mathematically, the energy needed to accelerate an object relates to its relativistic mass, which isn't a different mass but an effect of motion. As the object's velocity approaches light speed, its relativistic mass grows toward infinity. To push it from 99% of light speed to 99.99% demands an almost unimaginable amount of energy, more than the sun's total energy output over several years. This endless hunger for energy occurs because of Einstein's special relativity. The closer an object gets to the speed of light, the more its effective mass dresses up to resist acceleration. Think of pushing a wall that gets heavier the faster you try to push. No matter how strong your push, the mass's resistance increases, preventing reaching or surpassing that barrier. The energy needed approaches infinity, making it physically impossible to get there. Relativistic velocity addition further explains why nothing with mass can exceed the speed of light. Unlike simple addition, relativistic addition ensures that, regardless of your speed, you cannot surpass the cosmic speed limit, the speed of light as seen from any frame of reference. Massless particles like photons always travel at the speed of light. They do not try to accelerate to it, but are inherently built for that journey. Their entire existence is at that maximum speed, which they reach effortlessly. Objects with mass, however, are fundamentally different. They require propulsion, which becomes increasingly insurmountable as they approach light speed. Energy mass equivalence, expressed by E/mc2, indicates that energy and mass are interchangeable. As kinetic energy near infinity at high speeds, the total energy of the object also becomes infinite. This acts as a cosmic stop sign. Objects with mass cannot pass the speed of light. They are forever bound by this universal speed limit. This restriction is more than technical. It's fundamental to reality. The universe's structure enforces this limit to preserve causality, that causes precede effects and signals or information cannot travel faster than light. Surpassing this boundary would break the rules that maintain cosmic order and coherence. Physicists like Feynman uncovered the deep mathematics behind these constraints. Their work shows that the speed of light isn't just a high velocity, it's woven into the very fabric of spacetime. Any attempt to accelerate mass-containing objects towards or beyond that limit encounters an insurmountable barrier, an inseparable part of the universe's code. This ultimate speed limit is what keeps the cosmos ordered and consistent, even amidst our relentless curiosity and desire to go faster. Einstein's equation, E/mc2, encapsulates a profound relationship between energy and mass that reshaped our understanding of physics. It tells us that mass and energy are interchangeable. They're different facets of the same underlying reality. Here, E represents energy, m is mass, and c is the speed of light in a vacuum. The equation implies that a small amount of mass can be converted into a tremendous amount of energy, which is the principle behind nuclear reactions, and it reveals the intrinsic connection binding matter and energy together. This equivalence between mass and energy has profound implications for the universe's fundamental speed limit. Every object with mass possesses an inherent amount of rest energy, called rest energy, E/mc2. To increase an object's speed, additional energy must be supplied. Initially, this is straightforward. Applying a force accelerates the object, boosting it closer to the speed of light. However, as the object approaches this universal speed boundary, the energy required to continue accelerating grows disproportionately. The closer the object gets to the speed of light, the more energy is needed to increase its velocity, approaching infinity as it nears c. This leads to the pivotal insight. Reaching or surpassing the speed of light would demand infinite energy, an impossible feat, establishing the light speed barrier. This barrier fundamentally stems from the relativistic relationship between energy, mass, and velocity. Special relativity predicts that as an object accelerates near the speed of light, its relativistic mass, or more precisely its total energy, increases dramatically. From an external observer's perspective, the object's momentum and energy grow without bound as its velocity approaches c. To an observer, the object appears to gain mass, making additional acceleration increasingly difficult. From the object's own frame of reference, the laws of physics stay consistent. It always measures its own mass as constant, but from outside, the required energy to push the object faster skyrockets. This exponential increase in energy requirement manifests as a universal resistance to surpassing the speed of light. Instead of a physical wall, it appears as a cosmic difficulty terrain. The laws of physics encode this limit inherently. This ceiling is not just a technological hurdle but a fundamental principle enshrined in the structure of spacetime itself. Photons, particles devoid of rest mass, can travel at this speed, but any particle with mass cannot be accelerated to or beyond c. Doing so would require infinite energy, which the universe simply cannot provide. The light speed limit also explains why causality and the structure of spacetime are preserved. Faster than light travel would enable signals to arrive before they are sent, causing paradoxes and violations of cause and effect. Thus, the speed of light maintains the universe's causal order, ensuring consistency. In summary, Einstein's E-RMC2 reveals that mass and energy are interchangeable, and this relationship underpins the cosmic speed limit. As objects with mass accelerate toward light speed, their energy, and thus their relativistic mass, increases rapidly, approaching infinity at c. This makes surpassing or even reaching the speed of light impossible, because infinite energy is unattainable in our universe. The result is a fundamental boundary that shapes the universe's structure, governs the behavior of particles and cosmic phenomena, and ensures the preservation of causality. Light speed is not just a limit. It's a cornerstone of the universe's coherent, lawful fabric, deeply woven into the equations that define reality. One of the earliest experiments confirming the constancy of the speed of light was by Albert Michelson and Edward Morley in 1887. They used an interferometer to compare light's speed in different directions, expecting Earth's motion through the ether, a hypothetical medium for light, to cause detectable shifts. Surprisingly, they found no such shift. This null result implied that light's speed remained constant regardless of Earth's motion, challenging the idea of an absolute rest frame and paving the way for Einstein's special relativity. Later, the Kennedy-Thorndike experiment refined this, testing whether the speed of light varied over time as Earth's velocity changed. Using a more precise interferometer, they measured the speed at different times of year. Again, results showed no variation, reinforcing the notion of light's invariance. In the 1930s, Donald Topps and colleagues advanced these tests with masers, devices that amplify microwaves through stimulated emission. They compared frequencies of signals traveling different paths, finding consistent ratios over time and orientation. This provided further evidence that the speed of light does not depend on the motion of the source or the observer. Modern laser-based experiments offered even more precise confirmations. Laser interferometers capable of detecting phase shifts at parts in Tessendorf. Morse 15 consistently found that light in vacuum travels at a constant speed, unaffected by motion or source changes. These experiments represent the most direct and convincing evidence. Satellite-based tests, such as those involving GPS, also demonstrate light's constancy. GPS satellites synchronize clocks with astonishing precision, accounting for relativistic effects including the invariance of light speed. Without these corrections, the system would quickly fail, highlighting how crucial this principle is for modern technology. Astrophysical observations offer additional confirmation. High-energy events like gamma-ray bursts over billions of light-years show nearly simultaneous arrival of photons of different energies. If photons travelled at different speeds, we would observe dispersion or delays. Their synchronized arrival supports the idea that the speed of light remains unchanged across cosmic distances. From the 1880s to today, these experiments form a robust framework confirming that light speed is a fundamental constant. This principle is embedded in the fabric of reality, defying intuitive notions of motion. It underpins modern physics, from everyday technology to our understanding of the universe. The consistency across diverse methods, interferometric, massor comparisons, laser experiments, satellite measurements, and astrophysical observations, strengthens the confidence that the speed of light is invariant. Each successive test has increased measurement precision, yet all continue to support this fundamental fact. This extensive experimental evidence convincingly confirms that the speed of light in vacuum is unchanging, independent of the motion of sources or observers. Such empirical validation affirms Einstein's postulate and the core of relativity, shaping our understanding of space and time. The invariance of light speed is no longer a hypothesis but an empirically verified feature of the universe, essential for the consistency of physical law as we understand it. Many people imagine the speed of light as just a super-fast speed, like a race car zooming across the universe, but that's not quite accurate. A common misconception is that it's the ultimate speed limit. Nothing can go faster. While this idea is popular, The reality is that the speed of light in a vacuum is the fastest speed at which information or matter can travel, based on current physics. Objects with mass can accelerate close to light speed, but physics, especially Einstein's special relativity, prevents surpassing it. Another mistake is thinking anything can accelerate to reach light speed. It's not like revving a car to maximum speed. As an object accelerates toward light speed, its relativistic mass, or more precisely the energy needed, grows dramatically. To push an object with mass to light speed would require infinite energy, which is impossible, like trying to fill an infinitely large bucket with water. Instead, as objects get closer to light speed, they become increasingly resistant to acceleration and require exponentially more energy. That's why particles and accelerators reach only a fraction of light speed before their energy limits stop them. People also assume that because light travels at a fixed speed, it should be the same for everyone, no matter how they move. But in reality, the speed of light in a vacuum remains constant regardless of the observer's motion. Whether you're moving toward or away from the light source, you'll measure it travelling at about 300 million meters per second. This is one of Einstein's two postulates in special relativity, and defies everyday logic. Normally, if you run toward a moving object, you'd see it approach faster, but light always measures the same, no matter what. There's also misconception about what light is. Some think of it as tiny particles moving through space, others see it as a wave. In truth, light is electromagnetic radiation exhibiting wave-particle duality. Photons, the particles of light, have zero rest mass, which allows them to travel at the speed of light. They don't experience time or rest. They are pure energy packets that move continually at this cosmic speed limit. People might think the speed of light is just a constant, unaffected by the universe's conditions. But this constant arises from the structure of spacetime itself. While light slows down, passing through materials like glass, in a vacuum, its speed is fixed at about 300 million meters per second. It's a universal speed limit shaping the fabric of reality, not an arbitrary number dictated by technology or measurement. When we discuss a limit or max speed in physics, we're exploring a fundamental aspect of how our universe functions, affecting everything from tiny particles to the vast cosmos. At first glance, the idea that nothing can go faster than light seems simple. It's a well-known principle of relativity. But understanding what this speed limit truly means, why it exists, and its implications involves delving into physics, equations, and concepts that challenge everyday intuition. To clarify, a limit, or maximum speed, refers to the highest possible velocity objects can attain. In daily life, we see objects like cars or runners with upper speed possibilities, yet theoretically, they could go faster if technology allowed. In physics, however, the universe enforces an unbreakable cap on how fast information and matter can travel. The speed of light in a vacuum denoted c, approximately 292,158 meters per second. Though staggering by human standards, EAS is finite and fixed across the universe. This speed limit isn't just a number, it's woven into the core principles of relativity and space-time structure. Unlike arbitrary highway speed limits, the light speed limit emerges from the fundamental laws of nature. As an object with mass accelerates towards c, its relativistic mass increases exponentially, requiring ever more energy. Approaching c demands infinite energy, making it impossible for objects with rest mass to reach or surpass this boundary. The universal speed limit has significant consequences. First, it establishes causality, the principle that causes precede effects. If signals or influences could travel faster than light, it would be possible to send information backward in time, creating paradoxes like messages arriving before they were sent. Such scenarios threaten the logical consistency of physical laws and our understanding of time. Thus, the speed of a light acts as a cosmic speed governor, preserving cause and effect relationships throughout the universe. Beyond velocity, c underpins the Minkowski geometry of spacetime in Einstein's special relativity. Here, space and time form a four-dimensional fabric, with c serving as a conversion factor between spatial distance and temporal interval. This entanglement means fluctuations in one dimension influence others, and the maximum speed of causal influence is directly tied to c. No signal, force, or information can travel faster than this speed, preserving causal order and the stability of physical law. Photons, massless particles, always travel at exactly c. Their existence illustrates this speed limit's fundamental nature. It isn't just an arbitrary boundary, but a core feature of particle and force behavior. Particles with mass, like electrons or protons, can approach c asymptotically but never reach it. Their relativistic mass increases as they accelerate, requiring infinite energy for further acceleration, naturally preventing surpassing c. This resistance aligns with the principle that velocities are bounded in the universe. This speed limit influences our understanding of energy, momentum, and information dissemination. Electromagnetic waves, light, radio, X-rays, must obey this maximum in propagation. Gravitational influences, including gravitational waves, also propagate at c, ensuring effects are observed with a finite delay. This consistency guarantees that the universe operates predictably over vast distances and timescales, providing a stable framework for cosmology and physics. Moreover, the maximum speed constraint shapes technological applications from particle accelerators to communication systems and informs our grasp of the universe's evolution. The idea that no influence can outrun light preserves the causal, interconnected nature of the cosmos, preventing chaos and paradoxes. This universal speed limit embodies more than a physical constraint. It links energy, mass, space, and time. It maintains the causality chain, ensuring the universe's coherency. The fact that information and influence cannot surpass c fosters a universe where cause and effect are dependable, allowing physics to be formulated into elegant predictive theories. It functions as the cosmic heartbeat, an invariant that sustains the universe's order and harmony, balancing energy and information, preventing space-time from unraveling into chaos. In essence, the limit of speed in physics deeply influences the fabric of reality itself. It enforces the structure of space-time, upholds causality, and maintains the logical consistency of the universe. This speed cap means that no matter how advanced our technology becomes, the fundamental laws of nature constrain the maximum velocity. It ensures that signals, influences, and information can never outpace c, fostering an ordered, predictable universe. The idea of this limit aligns with Einstein's relativity, which revolutionized physics by interweaving space and time into a coherent whole. The invariance of c across all frames of reference ensures the consistency of physical laws and the preservation of causality. This universal speed limit is central not only to our understanding of light and particles, but also to the stability of the entire cosmos, from black holes to cosmic expansion. Ultimately, the speed of light symbolizes the fundamental limits rooted in the universe's structure. It unites the concepts of energy, space, time, and information, acting as the foundation of modern physics. This constraint ensures the universe remains orderly, with cause and effect relationships unbroken, enabling scientists to develop predictive theories about the past, present, and future. It is the cosmic speed limit that underpins the fabric of reality itself. 636 words. Imagine a universe without causality. That's a universe where cause and effect could dance out of sync, signals could skip backwards in time, and reality would unravel into chaos. That's why causality is so central to physics, especially regarding the speed of light. The speed of light isn't just a number, it's the cosmic speed limit that safeguards causality, ensuring cause always precedes effect. If information or signals could travel faster than light, an event happening here and now could influence a future event elsewhere in the universe at an earlier time. This would enable communication backwards in time, threatening the fundamental chain of cause and effect. Our notions of history, memory, and the sequence of events would be disrupted, leading to paradoxes like the grandfather paradox, where altering past events could prevent one's own existence. The speed of light acts as a cosmic gatekeeper. It creates a universal ordering of events, preserving causality. According to Einstein's special relativity, no information or matter can exceed this limit. This restriction maintains the cause and effect flow across the universe. If signals surpass the speed of light, observers moving at different velocities could disagree on the order of events, causing a breakdown in the objective reality that underpins consistency. This is not just philosophical. It's a fundamental aspect of the universe's logical coherence. Causal structure becomes clearer when visualized through light cones. Imagine the universe as a space-time grid. For any event, like flipping a switch, light radiates outward, forming a cone of influence. Anything inside this cone could be affected because signals travelling at or below light speed can reach those points. Outside the cone, events are causally disconnected. No information travelling at or below light speed can influence or be influenced by the initial event. If something travelled faster than light, it could cross this cone and reach points in space-time that should be causally unaffected or even influence the past. This creates paradoxes. In some frames of reference, the event appears to occur after its effect, flipping cause and effect. Such causal inversions threaten the fabric of reality, undermining the consistent temporal order. Einstein's theories forbid faster-than-light travel and reinforce that causality is woven into the very structure of space-time. The invariance of light speed, observed uniformly by all observers regardless of their motion, acts as an anchor for causality, ensuring its universal validity. This fundamental constant keeps the universe coherent, even as scientists explore the boundaries of what is possible. Beyond physics, causality underpins our everyday experience. It explains why popcorn pops after heating, why a thrown ball falls back down, and how memories form through cause and effect sequences. Without a consistent flow of cause preceding effect, life would resemble chaos, with no reliable pattern to guide understanding or action. In the universe's grand dance, the speed of light isn't just about how fast light travels. It's about maintaining the universe's coherence, ensuring cause precedes effect. Without this cosmic speed limit, reality as we know it, where actions lead to reactions and history unfolds in a logical sequence, would cease to exist. The universe needs its speed limit, not just to describe light's velocity, but to prevent paradoxes and confusion from spiraling into chaos. This profound link between the speed of light and causality forms the foundation of our understanding of reality. It preserves the logical structure of space-time, making possible a universe where cause and effect relationships hold true across vast distances and times. Without the speed of light setting the boundary, causality could break down, and the universe's fabric, its very ordering principle, would unravel. This relationship is so fundamental that it shapes the very fabric of existence, connecting the nature of light with the essence of cause and effect. 612 words. The idea of travelling faster than light has fascinated physicists and science fiction enthusiasts for generations. It promises a universe where we could traverse galaxies instantaneously, revisit the past, or communicate across cosmic distances immediately. Despite these enticing ideas, theories proposing faster-than-light travel or communication typically run into fundamental issues. Obstacles rooted in the fabric of our universe that often lead to contradictions, causality violations, and paradoxes. To understand why such theories break down, we must consider what happens when you attempt to exceed the universal speed limit, set by the speed of light. Einstein's special relativity states that as an object with mass accelerates toward light speed, its relativistic mass, or more accurately its energy requirement, increases toward infinity. You'd need an infinite amount of energy to reach light speed, making it impossible with finite resources. But what if, in a hypothetical universe, surpassing the speed of light was possible? This is where issues arise. Faster-than-light travel implies that, in some frames of reference, effects could occur before their causes, a direct violation of causality. Imagine a spaceship travelling faster than light. In one frame, it departs Earth today. In another, it arrives before it departs. This creates causal loops, events causing themselves or generating paradoxes. For example, a message could be sent to prevent an event, but that message might arrive after the event has already happened, reversing cause and effect. The tachyonic antitelephone illustrates this problem. Hypothetical particles called tachyons could, in theory, send signals into the past because in some reference frames, the signals arrive before they are sent. This could enable backward time communication, leading to paradoxes like the grandfather paradox, where one might prevent their own existence by interfering with the past. Such paradoxes threaten the logical consistency of the universe, as cause and effect appear to become unreliable. Beyond causality violations, faster-than-light theories challenge the fundamental structure of spacetime. Special relativity relies on the invariant nature of the speed of light, which divides causal and acausal phenomena. Surpassing this limit destabilizes this division. Mathematical models become unstable or nonsensical, leading to closed time-like curves, paths in spacetime looping back on themselves, allowing an object to revisit its past. While appealing in science fiction, These curves suggest the breakdown of predictability and logical coherence in our universe. Another obstacle is the conflict with quantum mechanics. Quantum entanglement might seem to suggest instantaneous effects, but it does not enable faster-than-light communication, thus preserving causality. Proposals for superluminal communication violate quantum principles and could produce paradoxes. For instance, they would allow instantaneous signaling across vast distances, contradicting the causality and locality principles underlying quantum theory. The hypothetical existence of faster-than-light particles or mechanisms, such as wormholes, introduces further complications. Wormholes are solutions to Einstein's equations, but they require exotic matter with negative energy density to remain stable. Their stability and traversability are purely theoretical. Even if such structures existed, traversing them would likely cause the same causality violations seen with tachyons, resulting in logical paradoxes and potential contradictions. Ultimately, the universe appears to strongly constrain us within a causal framework where faster-than-light travel is not just technologically impossible, but fundamentally incompatible with its structure. The paradoxes arising from attempting to surpass the speed of light aren't mere mathematical curiosities. They threaten the very foundation of our understanding of reality. They endanger the logical fabric that binds cause and effect, history and future. This reinforces the conclusion that the speed of light is the universal speed limit. Anything claiming to surpass it drags us into contradictions and paradoxes, leading to a universe that no longer behaves predictably or coherently, undermining the very nature of physical law. Imagine you're in a spaceship traveling through space. You fire up your engines, trying to go faster and faster. At first, it's exhilarating. Your speed increases, and you get closer to the universe's speed limit. But as you near the speed of light, something extraordinary happens. No matter how powerful your engines become, reaching or surpassing that cosmic barrier remains impossible. This isn't just a technological hurdle, it's woven into how our universe operates. That universal speed limit arises from Einstein's theory of relativity. It's not just about how objects move, it describes how space and time respond to motion. As you approach light speed, the rules change dramatically. Your mass appears to increase without bound, not because you gain more substance, but because your energy, related to your effort to accelerate, couples with your mass via rearchie. Near the speed of light, the energy needed to go faster skyrockets toward infinity. To accelerate even a tiny fraction closer to light speed requires infinite energy, making it impossible. This isn't just theoretical. Experiments support it. In particle colliders, electrons exhibit behavior predicted by relativity. Their effective mass increases as they near light speed, making further acceleration harder. No matter what energy is supplied, they never quite reach the speed of light. Instead, they get asymptotically close. The universe has built-in relativistic brakes that prevent anything with mass from surpassing that speed limit. Why does this boundary exist? It's rooted in space-time structure. Space and time aren't separate static entities. They form a four-dimensional fabric responsive to energy and momentum. Moving through space-time follows a world line. The speed limit constrains how quickly this world line can tilt or stretch. Approaching light speed makes the world line nearly vertical in space-time diagrams, leaving less room for spatial movement. The fabric's resistance to this tilting manifests as an infinite energy barrier, the fundamental reason no massive object can reach or exceed the speed of light. This speed limit also enforces causality, the principle that cause precedes effect. If particles or information could travel faster than light, the cause and effect chain could break down, leading to paradoxes where effects occur before causes. The relativistic speed ceiling preserves universal order, ensuring that information can't outrun causality. It creates a universal speed limit that's the same everywhere, for everyone. This absolute ensures the universe remains consistent and orderly. Moreover, relativity's limitations influence our understanding of particles. Photons, particles of light, always travel at the speed of light, not because they attempt to reach it, but because they are it. Their existence highlights that massless particles serve as messengers that move along space-time at this boundary. They illuminate the universe without ever crossing it. Objects with mass are confined to speeds below this threshold, by the need for infinite energy and by the intrinsic geometry of space-time. Concepts like time dilation also stem from this speed limit. As you near light speed, time for you slows relative to a stationary observer. This isn't just strange, it's a natural consequence of how velocities influence the flow of time within spacetime's framework. The universe's speed limit ensures that time maintains a consistent flow across the cosmos, adjusted by the relative motions of observers. The most profound aspect? This limit isn't just a practical boundary for space travel or physics labs, it's a fundamental feature of the universe's architecture. It shapes the laws of physics, constrains how matter and energy behave, and preserves cause and effect. The speed of light isn't just a barrier, it's a cornerstone of reality, encoded into the fabric of space-time. It reminds us that the universe is a finely tuned system governed by principles so profound that they challenge our deepest understanding of reality. This speed boundary enforces the logical consistency of the universe. Without it, notions of causality and the sequence of events would collapse. It ensures a universal order that underpins the fabric of existence. The constancy of the speed of light is embedded in spacetime itself, serving as a fundamental limit that preserves the universe's coherence. It's a core aspect of the universe's architecture that continues to influence physics, cosmology, and our understanding of reality. The speed of light isn't just a high-speed frontier, it's a fundamental aspect of the universe's structure, integral to how space, time, energy, and matter interact on every scale. 648 words. Space-time is a four-dimensional fabric woven from space and time, forming a single continuum. Rather than moving through space and time separately, objects travel along world lines across this fabric. This interconnected structure means objects, from electrons to stars, are following specific paths through space-time. Space-time isn't fixed. It interacts with mass and energy by bending, stretching, and rippling. Massive objects like stars create dents or curvatures in this fabric, similar to placing a heavy ball on a trampoline. These curvatures, perceived as gravity, shape how objects move and influence the flow of time. The geometry of spacetime guides motion in a consistent way. The speed of light signifies the universe's ultimate speed limit, rooted in spacetime's geometric structure. Within this fabric, geodesics, shortest and straightest possible routes, set boundaries for how objects move. Massive objects follow these paths, but nothing can cut across or hop over the fabric faster than the geodesics allow. Doing so would require surpassing a fundamental boundary, the fabric's horizon, an impossibility. When an object accelerates toward light speed, it's not just increasing its velocity through space, it's also altering its experience of space and time due to the fabric's properties. As speed increases, the object causes the fabric around it to stretch or tilt, reshaping space-time. To reach light speed, an object would need infinite energy, akin to stretching an infinitely elastic sheet infinitely far, a physical impossibility constrained by the fabric's geometry. The primary reason objects with mass can't reach or exceed light speed is because of spacetime's shape. As they accelerate, they require exponentially more energy due to relativistic mass increase. Near light speed, the energy needed approaches infinity. Geometrically, this translates to an infinite distance within the fabric, reflecting the universe's fundamental limits. Crossing this boundary would require breaking the fabric's inherent structure, which cannot occur. Furthermore, spacetime's nature enforces the speed limit through the invariance of the speed of light, the same for all observers, regardless of motion. Because this speed is universal, spacetime acts as a built-in ceiling, woven into the fabric of reality. Surpassing it would involve tearing or stretching the fabric in ways that violate physical laws, something impossible in our universe. The interplay of space and time creates a universe where motion, gravity, and causality are governed by the same geometric principles. Travelling along geodesics exemplifies how curvature constrains motion. The fabric's shape, the paths objects follow, and the constancy of the speed of light combine into a foundational law. The speed limit isn't arbitrary, but embedded in the structure of space-time. Within this woven fabric, the link between space and time forms the core of cosmic architecture. Attempting to accelerate past light speed is like trying to rip the fabric. The universe's intrinsic properties forbid it. This structure determines the maximum speed, energy limits, and causal boundaries, all rooted in the fabric's geometry. The fabric's curvature and geodesics reflect a universe interconnected through space-time. The constant speed of light acts as a natural barrier, a boundary woven into the universe's fabric, preventing objects with mass from exceeding it. Surpassing this boundary would require unattainable energies and distortions beyond physical possibility. This concept reveals how spacetime's geometry enforces the speed limit. As objects accelerate, they need exponentially increasing energy, approaching an infinite horizon near light speed. The universe's laws, woven into the fabric itself, limit this capacity, restrictions that are fundamental, not merely physical constraints. Understanding the speed limit through spacetime shows that this boundary is a reflection of the universe's underlying shape. Its geometry, with geodesic paths and invariance principles, naturally constrains motion. Trying to outpace light is equivalent to tearing or overstretching the fabric, an impossibility rooted in the universe's structure. This geometric perspective demonstrates the universe as a dynamic entity. Objects move within its fabric, constrained by its curvature, which determines what is possible and impossible. The speed of light emerges as a fundamental property, a cosmic boundary attached to spacetime's architecture. The interconnectedness of space and time creates a flexible yet constrained universe. The shape and properties of the fabric dictate maximum speed, shaping causality, energy, and motion. The invariance of the speed of light is woven into the fabric's essence, establishing the ultimate pace that cannot be exceeded. In summary, spacetime is central to understanding why nothing with mass can surpass the speed of light. Its curvature guides the paths objects follow. Its invariance enforces the cosmic speed limit. The fabric's boundaries and geometry fundamentally restrict motion and energy, making the speed of light a universal constraint embedded in the universe's structure. While most physics supports light speed as the ultimate limit, some phenomena challenge or complicate this idea, revealing that our universe may be more nuanced. These exceptions don't disprove the speed limit but open intriguing insights into the nature of reality. Quantum entanglement is one example. Two particles linked so that measuring one instantly reveals the state of the other, regardless of distance, leading Einstein to call this spooky action. At first, it seems information travels faster than light, violating the limit, but no usable information is transmitted through entanglement. The correlations cannot be harnessed to send messages instantaneously. They resemble a mysterious link that defies simple speed constraints without truly breaking the rule, hinting at a deeper underlying connection in the universe. Quantum tunneling is another phenomenon. Classical physics says a particle needs enough energy to climb over a barrier, but in quantum mechanics, particles can appear on the other side without having sufficient energy, thanks to their wave function. Tunneling can sometimes seem instantaneous, or faster than light when crossing thin barriers, with transitions effectively occurring in zero time. However, tunneling isn't controllable in a way that allows faster-than-light communication, so it doesn't violate relativity principles. Theoretical constructs like warp drives or spacetime shortcuts also challenge straightforward distance limits. The Alcubierre drive, for instance, involves contracting space ahead of a spacecraft and expanding it behind. Inside this bubble, the craft moves faster than light relative to external observers. Without locally exceeding the speed limit, it's space itself that moves. Such concepts require exotic matter with negative energy density, which is unknown in the required quantities. Still, they push the idea that faster travel might be possible by altering space-time, rather than breaking the speed limit directly. On a cosmic scale, the expansion of the universe can seem to surpass light speed. Distant galaxies aren't moving through space faster than light, but are carried away as space itself expands. This isn't a violation because the limit applies only to objects moving through space. The fabric of space-time stretching makes galaxies recede faster than light, reinforcing that the speed of light limit pertains to local motion rather than cosmic expansion. Tachyons, hypothetical particles always travelling faster than light, also pose a challenge. They would have imaginary mass and behave in ways that seem to defy causality. While no experimental evidence supports their existence, if they did, they might imply the universe admits superluminal entities, but at the cost of paradoxes and causality violations at the core of physics. Their potential existence raises profound questions about the basic structure of the universe. These phenomena do not outright overthrow the idea of light speed as a universal ceiling, but underscore the universe's complexity. They compel us to reconsider what speed truly means at quantum and cosmic scales. The universe isn't a simple machine with a hard limit. Instead, it's a tapestry woven with threads that sometimes challenge or appear to bypass that limit, yet always within the framework of underlying physical laws. They preserve causality and consistency in ways still being explored, revealing that our understanding of speed, space, and time is far from complete. Richard Feynman's contributions to light and quantum physics are transformative, revolutionizing how physicists understand fundamental interactions and the nature of reality. His work changed models of particle behavior, especially light, at the microscopic level. Before Feynman, scientists recognized light exhibited wave-like and particle-like properties, a duality that was a profound mystery. Waves explained interference and diffraction, while the particle perspective explained phenomena like the photoelectric effect. Reconciling these behaviors into a unified framework was a major challenge. Feynman approached this with fresh insight. He developed the path integral formulation, a way to visualize and calculate probabilities of particles traveling and interacting. Instead of particles following a single, definite path, he proposed that all possible paths contribute to the overall probability amplitude, each weighted by a phase factor related to the action, a key quantity describing a system's dynamics. In this framework, the behavior of photons and other particles emerges from summing all possible journeys between points. This was revolutionary because nature doesn't follow a single deterministic path, but rather a superposition of every possible path, each influencing the outcome. Most famously, Feynman introduced Feynman diagrams, visual tools that simplified complex calculations of particle interactions. These diagrams graphically represented interactions, such as electrons emitting or absorbing photons, making calculations more manageable. Each line and vertex corresponded to a particle process, providing a clear visual basis for the mathematics. This innovation made quantum electrodynamics, QED, the theory of light and matter interactions, more accessible and precise, enabling calculations that matched experimental results with extraordinary accuracy. Feynman's role in quantum electrodynamics is central to his legacy. QED describes how electrons and photons exchange energy and momentum, and it is among the most successful theories in physics. His contributions helped establish QED as a consistent, highly predictive framework. Prior to his work, physicists struggled to achieve such precise agreement with experiments. He also clarified the role of virtual particles, temporary mediators in quantum field theory responsible for electromagnetic interactions. Through diagrams, Feynman demonstrated that these virtual particles, though not directly observable, are fundamental in mediating forces between particles. This insight fundamentally changed our understanding of particle interactions and forces at the quantum level. Beyond these achievements, Feynman was a master communicator. His teaching style and enthusiasm made abstract quantum ideas more accessible. His lectures, later compiled into the Feynman Lectures on Physics, continue to inspire students and scientists alike, fostering curiosity and understanding of the universe's underlying principles. His curiosity extended beyond electrodynamics. He explored quantum computing, chaos theory, and the foundations of quantum mechanics. Yet, his primary contribution remains his groundbreaking work on light and particles at the quantum scale, through the path integral approach and the diagrammatic method. The elegance of his methods, their conceptual clarity, and unmatched predictive power distinguish Feynman. His insights revealed a universe built from probabilities, superpositions, and interactions occurring near the speed of light. His work showed the quantum world, where particles behave as waves and vice versa, could be understood through simple yet profound calculational tools. Feynman demonstrated that even complex phenomena could be explained with creativity, curiosity, and rigor. His work clarified light's quantum nature and emphasized the importance of visual intuition and mathematical elegance. His methods unlocked deeper secrets about the universe, offering a window into the hidden dance of particles that make up reality. His contributions show how the strange quantum realm can be described with simple, powerful tools. He revealed that the universe operates on probabilities, superpositions, and interactions at near-light speeds. His conceptual breakthroughs have shaped modern physics and continue to influence fields across science. When considering light and its behavior, Feynman's legacy is unmistakable. He showed the quantum world's dual wave-particle nature could be understood through elegant, accessible models. His work not only clarified how light interacts with matter at the quantum level, but also demonstrated the value of visualization and mathematical insight. Feynman's work exemplifies the power of curiosity and rigor in uncovering nature's secrets. His ideas transformed the way we view the microworld and inspired generations to explore the universe's mysteries. His revolutionary methods remain fundamental tools in physics, emphasizing that even the most complex phenomena can be understood through creativity, clarity, and determination. Richard Feynman approached the question of why light speed is the universe's ultimate limit with a blend of curiosity and deep insight. Unlike many who accepted Einstein's relativity as an elegant solution, Feynman wanted to understand what this speed limit genuinely meant, beyond pure mathematics. His approach aimed to probe the fundamental nature of the universe, revealing how it behaves at its most basic level. Feynman believed that the universe's laws should make sense, at least to a capable mind. As he explored light and spacetime, he combined intuitive reasoning with quantum mechanics. To understand why nothing can surpass light speed, he needed to rethink what speed truly represents at the deepest level, not just measure it. One of Feynman's key insights emerged from his work on Feynman diagrams and quantum electrodynamics, QED. When examining particle interactions at the quantum level, he realized that particles like photons are intrinsically tied to spacetime's fabric. Photons are massless, which makes them always travel at the same speed, light speed. Their behavior is dictated by the universe's electromagnetic structure. Photons act as messengers, moving through the fabric without mass, always at this constant speed. He considered the implications. A photon cannot be at rest in any reference frame. This invariance in speed is embedded in Maxwell's equations, which describe electromagnetism. These equations naturally lead to the conclusion that light speed is a universal limit. Feynman recognized that this wasn't a coincidence, but a consequence of electromagnetic symmetry. The equations demand that electromagnetic waves propagate at a fixed speed, and because photons are massless, this speed is absolute. But Feynman asked, why is that the case? Instead of accepting light speed as a given, he probed deeper. What does this velocity signify in the universe's structure? He understood that massless particles like photons can't be accelerated past their speed. They simply are bound to it by nature. Pushing a massive object beyond this limit would require infinite energy, a consequence rooted in Einstein's mass-energy equivalence. He explored causality, the idea that causes precede effects. Traveling faster than light would allow signals to travel backward in some frames, leading to paradoxes like the grandfather paradox. Feynman saw that the universe's restriction on superluminal travel preserves logical consistency. This maintains causality, preventing the universe from descending into chaos where cause-effect relationships could invert unpredictably. Furthermore, Feynman examined spacetime's quantum properties. He considered that the invariant light speed might be a fundamental feature of spacetime itself, described by Einstein's general relativity. The geometry of spacetime imposes this maximum speed as a geometric constraint woven into the universe's fabric. Changing this would mean warping spacetime or tearing the fabric, an impossibility without breaking the universe's structural rules. Feynman emphasized that the universe doesn't hide secrets. The speed limit is a consequence of symmetry, properties of fundamental fields, and spacetime structure. These aren't arbitrary rules, but inevitable truths about how the universe is built at its core. Just as gravity is an unavoidable feature of spacetime curvature caused by matter and energy, the speed limit emerges naturally from the universe's architecture. By combining quantum mechanics and relativity, Feynman helped reveal that the light speed limit isn't arbitrary, but rooted in the universe's structure. It's a boundary arising from the nature of particles, fields, and spacetime's geometry. Understanding this isn't merely knowing a number, about 300 million meters per second, but appreciating a profound symmetry that governs everything from tiny particles to cosmic expanses. Feynman's approach illustrated that questioning basic principles can deepen our understanding of the universe's elegant complexity. He invited us to see these limits not as arbitrary constraints, but as windows into the universe's intrinsic properties. These properties define the very limits of reality, anchoring the universe's structure and behavior at the most fundamental level. Feynman's path-integral formulation of quantum mechanics revolutionizes how we understand particle motion. Instead of particles following a single, definite path, Feynman proposed that, at the quantum level, particles explore every possible route from point A to point B. Some paths are direct, others meander wildly, looping and swirling through space and time. All these paths contribute to the particle's overall behavior, influencing its probability of appearing somewhere. The contributions of each path are governed by the action, which measures how a path behaves concerning energy and motion. When calculating the probability of a particle in a certain location, all paths' contributions are summed using complex numbers. Each path adds a phase, like a wave, that can reinforce or cancel with others. Paths resembling classical straight-line motion tend to reinforce each other, dominating the sum and aligning the behavior with classical physics predictions. This framework effectively includes quantum phenomena such as tunneling, where particles pass through barriers classically forbidden, and quantum interference, where waves amplify or diminish each other. The sum over all paths doesn't only replicate classical trajectories, but also includes many non-intuitive ones, some mathematically suggesting faster-than-light travel. However, these paths usually involve rapidly oscillating phases that cancel out, especially at energies typical in everyday physics. A key connection emerges between particle speed and the universal speed limit, the speed of light. When calculating amplitudes for a particle moving from A to B, all paths, including convoluted longer ones, are considered. Many of these appear to imply superluminal travel, yet their contributions interfere destructively, especially at observable scales, ensuring they don't influence measurable outcomes. The quantum action and relativity principles work together, favouring paths close to classical light-speed trajectories. Rapid phase oscillations from superluminal paths lead to cancellation, reinforcing the speed limit. Deeper still, the path integral perspective suggests particles don't merely move classically, they explore a universe of possibilities. Longer paths exceeding the speed of light resemble flickering shadows, possible in the mathematical landscape but rendered insignificant because of destructive interference. This accounts for why causality holds. The universe preserves cause and effect sequences, and signals can't travel faster than light. The structure of the quantum sum over paths subtly enforces this boundary, maintaining a consistent order. In high-energy phenomena such as particle collisions or cosmic rays, the path integral approach aligns naturally with special relativity. The sum over paths inherently respects the speed limit, because dominant contributions come from paths respecting it. The framework doesn't explicitly state no faster than light, but laws of quantum mechanics and relativity filter out incompatible paths. Those violating the speed limit tend to interfere destructively, leaving only physically meaningful paths that uphold the cosmic boundary. This insight reveals that the universe's speed limit isn't arbitrary. It emerges from deep quantum laws governing particles and waves. The paths, regardless of how winding, are structured so that the overall probability emphasizes paths respecting light speed constraints. The sum over routes resembles a symphony, with superluminal paths playing minor, cancelled-out notes, preserving harmony and causality. All experiments, particle collisions, cosmic rays, tunneling reflect this principle. Paths implying faster-than-light travel contribute minimally. Their effects cancel out through destructive interference. Governed by quantum laws, the universe acts as an invisible guardian of causality, ensuring cause-effect relationships remain intact. The harmony of quantum mechanics and relativity guarantees the speed of light as an unbreakable boundary. Feynman's path integral is more than a mathematical tool. It offers a new lens to understand the universe. The speed limit isn't an arbitrary rule, but a natural consequence of interconnected quantum and relativistic laws. The universe's possible paths, no matter how winding, are structured so that paths implying faster-than-light travel cancel out, maintaining causality and order. This framework captures the delicate balance between the probabilistic quantum world and the relativistic speed limit, showing that the speed of light acts as a fundamental barrier, not an obstacle, but an intrinsic feature of quantum reality. Paths exceeding the speed of light resemble flickering shadows, possible mathematically, but rendered insignificant because of interference. The quantum sum over paths ensures signals and causal relationships are preserved, aligning with Einstein's relativity. The universe's speed limit arises naturally from quantum laws, not as an imposed restriction, but as a fundamental consequence of particle-wave behavior and the sum over history's principle. This consistency across scales indicates the speed limit is woven into the universe's fabric. In essence, Feynman's formulation demonstrates that what we observe, particles moving at or below light speed, is a result of quantum superposition. Destructive interference of superluminal paths prevents them from manifesting physically, thereby preserving order and causality. The universe's laws operate as an intricate symphony where faster-than-light notes cancel out, emphasizing a universe governed by probabilistic quantum behavior and relativistic constraints. From this perspective, the universe is a harmonious whole, where quantum laws and relativity discipline possible paths, ensuring superluminal travel remains a mathematical curiosity rather than physical reality. The quantum state sum enforces the light speed limit, making it an elegant feature woven into the quantum tapestry. Thus, the speed of light isn't just a technological boundary, but a fundamental aspect emerging from the quantum nature of reality, as revealed by Feynman's formulation. Paths exceeding light speed act like flickering shadows, possible in the mathematical landscape but insignificant in reality because interference cancels them. The structure of the quantum sum over paths guarantees that signals and causal relationships adhere to the speed limit, aligning with relativity. The universe's law of the speed limit isn't an arbitrary rule, but results naturally from quantum principles governing particle-wave interactions and the sum over history's approach. This indicates the speed of light is an essential feature deeply rooted in the quantum fabric of the universe. In summary, Feynman's path integral shows that particles move at or below the speed of light, because destructive interference cancels paths suggesting otherwise. The laws of quantum mechanics and relativity work together to maintain causality and order. The universe operates as an elegant symphony, where potential faster-than-light notes are muted by interference, ensuring the speed of light remains an unbreachable horizon. This deep connection confirms that the speed limit is a natural outcome of the universe's quantum structure, not merely an imposed boundary. Richard Feynman, the legendary physicist known for his ability to make complex ideas seem almost playful, approached the nature of photons with a remarkable clarity that still sparks curiosity today. To Feynman, photons are not just tiny particles flying through space. They are messengers, carriers of energy and information that dance along the fabric of the universe at the ultimate speed, light speed. He starts by emphasizing that photons are massless particles. Unlike everyday objects, cars, planets, or even baseballs, photons have no rest mass. This is a crucial detail because it fundamentally influences their behavior. Without mass, they do not experience inertia in the traditional sense, and they must always travel at a constant speed. That speed? Exactly 300 million meters per second in a vacuum. Nothing faster, nothing slower when they're on the move. Feynman then points out something mind-bending. Photons are quantum objects. They exhibit both wave-like and particle-like properties, a duality that puzzled scientists for decades. When you observe them as particles, they appear as discrete bundles of energy. But as waves, they spread out and interfere, creating patterns that reveal their wave nature. This dual nature isn't just a quirky trait, it's woven into the fundamental rules of quantum mechanics, setting photons apart from the familiar objects we encounter daily. He explains that photons are produced whenever charged particles, like electrons, accelerate or decelerate, or whenever atoms jump between energy levels. Think of electrons as tiny sparks. When they move from one energy state to another, they release or absorb photons. This process is how light and other electromagnetic radiation are born. But the real kicker is that the energy of a photon isn't arbitrary. It's directly proportional to its frequency. The higher the frequency, the more energetic each photon becomes. That's why gamma rays, with their incredibly high frequencies, pack a punch, while radio photons are more gentle. Throughout his discussion, Feynman highlights that photons obey Einstein's special relativity without breaking a sweat. Their speed is invariant, meaning no matter the observer's motion, they always zip along at exactly the same speed. This constancy isn't just a quirky trait, it's woven into the core of the universe's structure. Imagine riding in a spaceship travelling close to light speed. When you look out the window at the photons zipping past, they're still blazing at that 300 million meters per second, unchanging and unwavering. Einstein's magic comes into play here. No matter how fast you go, photons don't lag behind or speed ahead. They are the universe's speedometers, calibrated to the same speed everywhere. Feynman also explores what this means on a deeper level. Because photons travel at this fixed speed, they dictate the maximum pace at which information and influence can propagate. This limitation is why faster-than-light travel is so problematic. Anything attempting to surpass light speed would require infinite energy, like trying to push a car uphill forever. Photons, in a way, are the universal speed limit guardians. Everything that carries information, massless or not, must abide by their constant, unbreakable velocity. He caps the discussion by emphasizing that light speed isn't just a steady number. It's a fundamental property woven into nature's very fabric. Photons, as carriers of electromagnetic force, serve as the bridge linking the quantum and the relativistic worlds. They embody the universe's unyielding rule. Nothing with mass can reach or exceed light's swift, unbreakable pace. As Feynman often did, he invites us to marvel at the elegant simplicity of this rule, knowing that even in its simplicity lies profound complexity, a universe that dances to the rhythm set by the tiniest, most mysterious travelers, photons. Imagine a world where light isn't just a steady wave or a little packet zipping through space, but a complex, unpredictable dance governed by the quirkiest rules of quantum mechanics. That's exactly what Richard Feynman unraveled, a revelation so mind-melting that it shook our understanding of light itself to the core. Up until Feynman's insight, everyone believed photons, the fundamental particles of light, behaved nicely, following predictable paths. But what Feynman uncovered was far more astonishing. At the quantum level, light doesn't simply travel from point A to point B in a straight line. Instead, it's more like a symphony of countless possible journeys, all happening simultaneously. Feynman introduced a revolutionary concept called the sum over histories, or sometimes the path integral formulation. Think of it like a cosmic roulette wheel. When a photon travels from a source to a detector, it doesn't pick just one path. It explores every conceivable route, zigzagging, looping, even sneaking through the tiniest gaps in space, and each of these paths contributes to the final outcome. It's as if the photon is a superstar performer trying every move on stage, no matter how unlikely, in the hopes that all these efforts somehow sum up to produce what we see and measure. But how does that work? How can all these impossible paths influence reality? Feynman showed us that each of these paths has an associated probability amplitude, a kind of quantum score, which can add or cancel out other paths depending on the circumstances. When you look at the overall picture, certain paths reinforce each other, making some outcomes more likely, while others cancel each other out entirely, making those outcomes vanish from our experience. This is the core of quantum interference, and it's what makes light's behavior so bizarre and beautiful. Now here's the wild part. In classical physics, particles follow specific trajectories, and you can predict where they'll go with some certainty. But in the quantum realm, light loses that deterministic leash. Its behavior becomes inherently probabilistic. Feynman's work showed that, at its heart, light is a superposition of all possible histories, each contributing to what we ultimately observe. There's no one path that photons take, only a weighted blend of every conceivable journey. This completely upends our intuitive understanding of motion and causality, flipping it on its head. What's even more mind-blowing is how this quantum perspective ties into the fabric of reality. It explains phenomena like diffraction and interference, the very reason light spreads out when passing through tiny slits or creates those mesmerizing patterns on a soap bubble. These effects are direct consequences of multiple paths interfering, reinforcing some outcomes and cancelling others. In effect, the universe is a giant quantum orchestra, where every possible note and variation contributes to the grand symphony of reality. But there's a profound truth buried deep here. The nature of light at the quantum level suggests that the universe isn't as straightforward as our everyday experiences imply. Instead, it's an intricate web of probabilities, orchestrated by an almost poetic dance of all possible histories. The universe doesn't just choose one path for light to travel, it considers everyone, and through the magic of quantum interference, the paths that align perfectly blend into the light we see. Feynman's discovery reveals that light, at its most fundamental level, is a symphony of probabilities, an understanding that opens doors to the weird, wonderful, mind-melting universe of quantum mechanics. It's a reminder that the world isn't always what our senses tell us, and that beneath the surface of reality is a cosmic ballet of possibility, forever unfolding in ways that continue to astonish even the greatest minds. Richard Feynman, one of the most brilliant and curious minds in physics, unlocked a lot of the universe's secrets through his work on quantum mechanics and particle physics. When we delve into how his insights connect to the universe's fundamental speed limit, light speed, we open a doorway to understanding why nothing can go faster and what that really means for the fabric of reality. Feynman was particularly fascinated by the nature of particles and the way they interact at the quantum level. One of his most significant contributions was his development of Feynman diagrams, visual tools that explain how particles exchange energy and momentum. These diagrams aren't just artistic sketches. They encode the probabilities of every possible interaction. They show us that at the quantum level, particles don't just interact in a straightforward way. Instead, they dance through a myriad of paths, each contributing to what we observe as a single event. Here's where the connection to the universe's speed limit becomes clear. When Feynman examined the behavior of particles, especially photons, the particles of light, he uncovered that their speed is not just a number, but a fundamental feature woven into the laws of physics. The universality of light's speed emerges naturally within the framework of quantum electrodynamics, the quantum theory of electromagnetic interactions that Feynman helped develop. Photons are massless particles, and their masslessness is what guarantees they always travel at that absolute speed limit, light speed. But Feynman didn't stop there. His explorations into the quantum world revealed that the very structure of space and time is affected by the behavior of these particles. The way particles propagate, how they transmit forces, and their probabilistic nature link directly back to Einstein's relativity, where speed limit and causality are core principles. Feynman's diagrams show that as particles approach the speed of light, their energy requirements skyrocket to infinity. Nothing with mass can reach that point because it would require an infinite amount of energy. This insight directly echoes the idea that accessible speeds are bounded. Nothing can surpass light speed because the fundamental energies and probabilities involved become impossible to realize. What Feynman's work unveils is that the speed limit isn't just an arbitrary barrier, but an intrinsic consequence of the universe's quantum structure. It's a built-in feature of how particles, forces, and space-time itself are designed. When particles exchange photons, they transmit information at light speed, preserving causality, the cause always happening before the effect. This limits how quickly something can travel or communicate, maintaining a consistent and logical universe. If faster-than-light travel were possible, causality could break down, leading to paradoxes where effects could precede causes, creating visualized contradictions that defy everything physics stands for. Feynman's insights clarify that the speed of light acts like a cosmic speed bump. It's not just about how fast photons move, but a reflection of the universe's deepest rules woven into the probabilistic quantum fabric of reality. The impossibility of surpassing this limit ensures that the universe remains consistent, that information flows in a well-ordered manner, and that cause and effect maintain their proper sequence. When we push closer and closer to this boundary, through particle accelerators and experiments, we see that energies and probabilities behave in ways that reinforce the fundamental nature of the limit. These aren't just technological hurdles, but profound reflections of how the universe operates at its deepest level. Feynman's insights bring a nuanced understanding that speed isn't just about the velocity of a thing, but about the very framework of how the universe allows different particles and forces to interact. The universe's ultimate speed limit, therefore, isn't just a ceiling. It's a feature that ensures the coherence and causality that keep reality from descending into chaos. It's embedded in how particles wave, interact, and propagate, an elegant rule that maintains the universe's order at the most fundamental levels. The sonorous whisper of photons traveling at that unwavering speed is a testament to the universe's deep-seated harmony, unveiled through Feynman's groundbreaking perspectives. Quantum mechanics initially appears to challenge classical ideas of speed. Classical physics, Newton's laws and Einstein's relativity, set firm limits. Objects with mass can approach, but never reach, the speed of light. They move along well-defined trajectories, and their velocities can be measured precisely. Quantum mechanics introduces complexity that questions these notions, revealing a universe where the concept of speed is probabilistic and intertwined with reality. In the quantum realm, particles are described by wave functions, mathematical entities encoding probabilities. Instead of definite positions and momenta, quantum mechanics provides a spread of possible states, making the idea of a precisely measured speed less straightforward. For example, an electron in an atom doesn't move in a fixed orbit, but exists as a probability cloud, where its position and velocity are uncertain. Consequently, speed becomes a range of probable velocities rather than a single constant. Quantum tunneling exemplifies how quantum phenomena challenge classical concepts of speed. A particle encountering a potential barrier, which classical physics forbids crossing, can appear on the other side without travelling over the barrier conventionally. To our classical intuition, it looks like faster-than-light motion. However, it's a probabilistic event where the particle's wave function leaks through the barrier. Its presence is spread out, and this seeming superluminal behaviour is better explained by the non-local nature of quantum wave functions, which do not obey classical locality. Entanglement adds further complexity. When two particles are entangled, measuring one immediately determines the state of the other, regardless of distance. This instantaneous correlation suggests some form of faster-than-light connection. Still, it does not transmit usable information faster than light, respecting relativistic causality. Entanglement blurs classical notions of locality and causality, indicating relationships between quantum systems are more subtle than their classical counterparts. Quantum field theory, QFT, merges quantum mechanics with special relativity, aiming to reconcile these issues. In QFT, particles are seen as excitations of underlying fields spanning spacetime. These fields obey relativistic constraints, ensuring signals or causal influences do not surpass light speed. Photons, quanta of the electromagnetic field, travel at the speed of light, aligning with classical expectations. Though quantum effects introduce probabilistic and non-local phenomena, the transfer of information remains limited by light speed, preserving causality. Conceptually, quantum mechanics complements classical notions by adding depth. It shows that the universe is not deterministic, but a probabilistic fabric where particles can tunnel, fluctuate, and be correlated across distances. These phenomena challenge classical intuition, revealing a richly interconnected reality governed by principles that complicate straightforward ideas of velocity. Despite these challenges, the universe's speed limit remains intact. No known quantum process allows superluminal communication or causal paradoxes. The speed of light continues to set the universal boundary for information transfer. Quantum effects show that the meaning of speed is nuanced. It's intertwined with wave functions, fields, and probabilities, rather than being a fixed velocity along a trajectory. Quantum mechanics challenges the classical idea that speed is a straightforward, measurable property for particles moving predictably. It replaces this simplicity with a framework rooted in probabilities, non-local correlations, and the nature of measurement. This framework redefines how we understand velocity, emphasizing that causality and information flow, rather than raw velocities, are fundamental. While quantum effects reveal more complex notions of speed, they do not negate the classical bounds. Instead, they expand our understanding, showing that the universe's speed limit is part of a richer structure. The universe obeys the cosmic speed limit, but within a tapestry of probabilities and interconnectedness that redefine what it means to move. In essence, quantum mechanics broadens and deepens the classical understanding of speed. It demonstrates that velocity is not always a fixed, deterministic quantity, but often probabilistic and influenced by non-local correlations. These phenomena reframe our concept of motion, emphasizing the primacy of information transfer, causality, and quantum connectedness in defining the universe's speed limits. The classical view of particles moving along fixed paths at well-defined velocities is replaced by a universe where movement is governed by probabilities, wave functions, and field interactions. Quantum principles show that what we perceive as speed is driven by underlying processes embedding motion within a probabilistic structure. This interconnected fabric ensures the speed of light remains a fundamental boundary, even as the meaning of speed itself is expanded. Ultimately, quantum mechanics challenges the notion that speed is a straightforward measurable property. It redefines motion as a complex interplay of probabilities, non-local correlations, and measurement effects, all consistent with the universal speed limit. Chaos and coherence coexist at the quantum level, revealing that the essence of movement and velocity extends beyond classical intuition. The universe's speed limit persists, but within a framework where causality, information, and interconnectedness are more nuanced. The relationship with speed reflects quantum principles, where probabilities and entanglement interact with relativistic constraints. The classical notion of speed as a simple, measurable quantity is replaced by a richer understanding embracing the probabilistic and interconnected nature of reality. The quantum perspective reveals a universe that, while respecting the cosmic speed limit, operates within a more complex and fascinating framework, one where movement is woven into quantum fields, wave functions, and the flow of information. This underscores the idea that speed, in the quantum realm, is a notion intertwined with the fabric of reality, fundamentally different from classical measures. Entanglement and non-locality are among the most mind-bending phenomena uncovered by quantum mechanics, yet they challenge our classical intuition about how the universe should behave. Imagine two particles that, once interacted, become tangled in such a way that their properties are linked no matter how far apart they are. If you measure one particle to determine its spin, position, or polarization, the state of the other particle seems to instantly adjust itself, even if the second particle is as far away as a galaxy. It's as if, in some mysterious way, they communicate faster than light, defying everything we've come to understand about causality and speed limits. This phenomenon, known as entanglement, doesn't mean that information is traveling between particles instantaneously in a way that could be used to send messages faster than light. Instead, the entangled particles are part of a single, unified quantum system. When you perform a measurement on one part, you're not sending a message. Rather, the entire state collapses into a set of correlated outcomes. The particle's properties are correlated in a way that can't be explained by any classical local theory, hence non-locality. Non-locality suggests that the universe at its quantum core can produce correlations that seem to reach across space-time instantaneously, but crucially, these correlations cannot be used to transmit usable information faster than light. This is a crucial point. The shaking question for physicists has always been whether this non-locality messes up our understanding of causality. The idea that cause must come before effect within a causal chain limited by light speed. The answer turns out to be no, because while entanglement produces correlations that are instantaneous, it doesn't permit the kind of communication that would violate the cosmic speed limit. If you try to use entanglement to transmit messages, the outcome on each side is random. You can't control it in a way that encodes a message. So, even though the particles are correlated faster than light, this spooky action at a distance, as Einstein famously called it, can't be harnessed to send signals or information across space faster than light. And this is where the very heart of quantum mechanics reveals its profound subtlety. The universe is non-local in its quantum depths, yet it respects the relativistic boundary that no usable information can travel faster than light. It's a paradox that has puzzled scientists for decades, yet it fits perfectly within the framework of what quantum theory predicts and experiments confirm. These correlations are built into the fabric of quantum entanglement, a kind of order that exists beyond our classical notions of space and time. They show us that, on a fundamental level, the universe is more interconnected than it appears, with entanglement acting like invisible threads, linking distant points in a web woven from the fabric of quantum states. What does all this mean for our understanding of light speed as a universal speed limit? It emphasizes that the limit is not about how the universe is connected at a fundamental level, but rather about how information, causality, and physical influence operate within it. Light speed remains the ultimate speed at which cause and effect can influence anything that we, as observers, can control or observe. Entanglement and non-locality reveal that the universe's deepest quantum structure involves correlations that transcend classical notions of locality. Yet these correlations do not send signals or violate the causality constraint inscribed by the light speed limit. So, if you think about the universe as a grand cosmic dance, entanglement is like an invisible, instantaneous whisper between dancers, something that connects them beyond the space between, yet without breaking the choreographed rhythm set by the speed of light. It's a reminder that our universe holds secrets about connection, causality, and the very nature of reality itself. Secrets that keep challenging and expanding our understanding of what is truly possible. Wave-particle duality challenges our intuitive understanding of particles and waves. Traditionally, particles are tiny, localized objects with definite positions, while waves are spread out, oscillating entities extending through space. In quantum mechanics, these distinctions blur. Electrons, photons, and other particles exhibit both particle-like and wave-like behaviors depending on observation. This duality is fundamental to reality and directly influences our understanding of the speed of photons. photons are quanta of electromagnetic radiation, particles of light that also behave as waves of oscillating electric and magnetic fields. Saying a photon travels at the speed of light describes a property arising from its wave-particle duality. Imagine a wave in a pond. It has a wavelength, a frequency, and a speed, the rate at which the crest moves. For a photon, its wave aspect is characterized by a wavelength inversely related to its energy, through just E-chefs, where overall est is Planck's constant and just the frequency. What makes this intriguing is that, unlike classical particles, a photon's speed doesn't vary. It always travels at exactly light speed. Its wave nature means its wave function extends through space, but this doesn't imply the photon is spread out traditionally. Instead, the wave function encodes probabilities of detection locations, an inherently probabilistic aspect tied to its wave-like behavior. The photon's wave function is connected to the electromagnetic wave it embodies, oscillating fields propagating through spacetime. When emitted, such as during an electron transition, it releases electromagnetic energy moving at this universal speed. Its wave-like nature dictates that this energy disperses and propagates as a wave with a specific frequency and wavelength, yet as a quantum particle, it remains localized enough to be detected as a discrete energy point. Wave-particle duality becomes especially evident in phenomena like diffraction and interference, classic wave behaviors. Light passing through a slit or around obstacles produces interference patterns, hallmarks of wave behavior. Meanwhile, individual photons hitting a detector accumulate, revealing their particle nature. These behaviors aren't contradictory but rather complementary expressions of the same quantum entity. The relation to the photon speed is fundamental. Being massless, photons are constrained by space-time structure. Their wave functions are solutions to Maxwell's equations, describing electromagnetic wave propagation in free space. These solutions show that wave packets, localized groups of waves, move at light speed. Attempts to slow them down are futile because their nature is embedded into space-time itself. Their wave aspect ensures their propagation speed remains fixed to this universal constant, linking quantum behavior directly to classical speed limits. This explains why photons always travel at light speed. Their wave properties describe how they spread, interfere, and propagate. Their particle aspect determines where energy transfer occurs. Both are inseparable facets, representing a single dual entity. The evolution of the wave function guarantees this constant speed, invariant across all frames, consistent with special relativity. Moreover, wave-particle duality means photons don't choose their speed. Their existence as quantized electromagnetic excitations inherently constrains them to move at light speed. Accelerating or decelerating a photon would require changing electromagnetic wave structures, impossible in free space without altering physics itself. This balance, wave character giving wavelength and frequency, particle aspect delivering energy in discrete packets, illustrates the inseparability of the dual facets. The universe embeds this maximum speed into the very nature of photons. They are ripples in space-time that can never go slower or faster. Their duality underscores that the speed of light isn't just a boundary for massive objects, but an intrinsic property of quantum fields. The wave aspect explains how a photon propagates through space, including interference and diffraction phenomena, while the particle aspect ensures it delivers quantized energy. Both facets are crucial, inseparable parts of the same quantum reality. The speed of light becomes a fundamental marker, connecting quantum fields with the fabric of space-time, a universal speed limit, an embedded property of what a photon is, a ripple in space-time forever moving at this pace. Ultimately, wave-particle duality reveals that the photon's behavior, oscillating as a wave, detected as a particle, is a unified expression of the same underlying reality. This duality is not conflicting but complementary, with the speed of the photon serving as a bridge between the quantum and classical worlds. The constant speed of light reflects a deep unity, where the fabric of the universe guarantees the wave-particle duality operates within fundamental unchangeable limits, embodying harmony at the intersection of quantum mechanics and relativity. Exactly 616 words. Now, you might wonder, can quantum tunneling or other strange quantum phenomena happen faster than light without breaking the rules of physics? It's a question that tickles the curiosity of anyone who's delved into the weird world of quantum mechanics. The answer is both fascinating and nuanced, revealing how the universe's rules are more flexible than they might seem at first glance. Let's start with quantum tunneling. Imagine a particle, say an electron, approaching a barrier it classically shouldn't be able to cross because it doesn't have enough energy. Surprisingly, quantum mechanics says that there's a non-zero probability that this particle will suddenly appear on the other side of the barrier. It's as if the particle can magically tunnel through, appearing instantly beyond the obstacle. But does this mean it's breaking the light-speed barrier? Not quite. Although the tunneling process can involve very short timescales and, in some interpretations, looks like the particle is crossing the barrier faster than light would in free space, it doesn't allow for the transmission of useful information faster than light. This is a crucial point. The rules of relativity tell us that no information or signal can travel faster than light, because doing so would mess with causality, the cosmic order that keeps cause before effect. Quantum tunneling may make particles appear to beat the light speed, but this isn't a communication channel or a way to send messages faster than light. It's more of a quantum weirdness, where the particle's probability wave spread out, and the tunneling event is a reflection of its wave function's properties. This subtlety preserves causality. While the wave function's effect can be non-local, meaning they involve correlations over distances that seem instantaneous, the actual transfer of information remains bound by the cosmic speed limit. Think of it like a quantum whisper. The universe hints at correlations that appear to instantaneously connect distant points. But when it comes to transmitting meaningful data or signals, the speed of light reigns supreme. This quantum entanglement, often called spooky action at a distance, doesn't allow for faster-than-light communication either, because measuring or manipulating the entangled particles still obeys the relativistic constraints. But what about other phenomena that seem to challenge the light speed limit? Sometimes, in high-energy physics experiments, particles are observed to appear to move faster than light, often due to measurement artifacts or the way data is interpreted. A classic example involves Cherenkov radiation, where charged particles travel through a medium faster than light can travel through that same medium. It's important to clarify that nothing is exceeding the cosmic speed limit here. The particles are just outpacing light within a particular substance, not in the vacuum of space where the universal speed limit applies. Meanwhile, the fabric of spacetime itself, governed by Einstein's general relativity, strongly constrains how information and causal influences propagate. Even with the strange dance of quantum effects, the universe has built-in guardrails to prevent any violation of causality or faster-than-light communication that could unravel the fabric of reality. In some speculative theories, like certain interpretations of quantum gravity or ideas involving wormholes, the possibility of shortcuts through spacetime appears alluring. But these concepts remain theoretical and require conditions far beyond what we can currently achieve or observe. For now, the laws of physics, as our best understanding suggests, maintain that while quantum phenomena can seem to dance faster than light in their own strange way, the actual transmission of information, signals, or causal influence cannot. So, yes, quantum tunneling and other quantum phenomena can look like they're happening faster than light, but they don't violate the core principles of physics. Instead, they reveal just how intricate, counterintuitive, and yet beautifully consistent the universe really is. The universe's rules are strict, but they also allow for this mysterious, wondrous quantum choreography, a dance where the speed limit of light remains, unchanged and unbreakable, yet the universe's underlying fabric remains deeply interconnected in ways that still puzzle and inspire us. The uncertainty principle, introduced by Werner Heisenberg, is one of the most profound insights in quantum mechanics, and it plays a crucial role in how we understand the behavior of particles, especially when it comes to their speeds and motions. To grasp its significance, imagine trying to pin down a tiny particle like an electron traveling through space. When we measure the particle's position with great precision, we inevitably introduce a level of uncertainty in its momentum, which directly relates to its speed. Conversely, if we attempt to measure its momentum very precisely, then our knowledge of where it is becomes fuzzy. This intrinsic limit isn't just due to measurement imperfections, it's baked into the fabric of quantum reality itself. Now, how does this relate to the idea of maximum speeds? When we consider particles zooming close to the speed of light, the uncertainty principle introduces a fascinating twist. As a particle's energy increases, say because it's moving faster and closer to light speed, the uncertainties in its properties also become more pronounced. Specifically, as the particle's energy grows, it becomes harder to define its exact position and velocity simultaneously. This isn't just a technical inconvenience, it has profound implications. Let's delve deeper. According to the principles of quantum mechanics, particles aren't really tiny points moving along precise trajectories. Instead, they are described by wave functions, which give us probabilities of finding the particle in particular places and with particular momenta. The more we try to localize a particle in space, the greater the spread in its momentum. When a particle nears light speed, its momentum becomes extremely large, and the wave function's spread in momentum space widens. This means there's an inherent unpredictability about its exact speed at any given moment. What does this have to do with the speed limit? Well, it highlights the fact that particles cannot be sharply defined with both position and velocity, especially as they approach high energies near the speed of light. The uncertainty principle imposes a sort of fundamental fuzziness that prevents particles from having infinitely well-defined speeds. If one hypothetically tries to push a particle's speed beyond the speed of light, these quantum uncertainties would become unmanageable, and such a scenario would conflict with the core tenets of relativity. Furthermore, the uncertainty principle underpins why no particle with a non-zero rest mass can be accelerated to light speed. As the particle's energy increases, the wave function describing it becomes more and more spread out, making the precise measurement of its speed increasingly uncertain. But approaching the light speed barrier also requires infinite energy, something that quantum uncertainty makes conceptually consistent with the idea that the particle's behavior becomes fundamentally unpredictable at those extremes. In addition, the principle helps explain why particles cannot break the light speed limit in a classical sense. The more we try to speed up a particle, the more its quantum wave function resists confinement to a precise velocity that exceeds this universal constant. The uncertainty principle acts as a natural safeguard. It ensures that any attempts to surpass the speed of light would encounter such overwhelming quantum unpredictability that, practically speaking, it becomes impossible. So, in the grand cosmic game where particles dance at the edges of what physics allows, the uncertainty principle isn't just a quirky quantum rule, it's a key piece of the puzzle that enforces the cosmic speed limit. It prevents us from having perfectly defined, infinitely precise knowledge of a particle's velocity, especially near the speed of light, and, in doing so, helps preserve the causal and relativistic structure of the universe itself. Our universe's speed limit isn't just about energy and spacetime geometry. It's also about this fundamental quantum fuzziness that keeps everything in check, ensuring that the cosmic speed cap remains unbreakable. Imagine a universe where particles are connected in ways that seem to defy the very fabric of space and time. Bell's experiments do exactly that. They peel back the curtain on the nature of reality, challenging our deepest assumptions about how the universe operates at its most fundamental level. At the heart of Bell's tests are pairs of particles that are generated in such a way that their properties are entangled. This means that the state of one particle instantaneously influences the state of its partner, no matter how far apart they are. You might think, well, if these particles are light years apart, how can a change in one affect the other instantly? It's as if the universe has a secret rule, a mysterious connection that transcends the usual ideas of speed and locality. Under the framework of classical physics, we'd expect no influence to travel faster than light. If you measure the state of a particle here, the measurement should only affect things within its causal neighborhood, respecting the cosmic speed limit. Bell's experiments, however, show something different. When scientists measure entangled particles, the results are correlated in ways that can't be explained by any local, classical mechanism. No hidden signals zipping between the particles at or below light speed. These correlations aren't just random, they violate what's known as Bell's inequalities, mathematical boundaries that impose limits on what could be explained by local hidden variables, hidden factors hidden from our view that might determine the particle's properties in advance. Yet, repeated experiments strip away those classical explanations. The only viable conclusion is that the universe inherently links these particles in a way that isn't bound by the speed of light or traditional notions of locality. This realization forces us to rethink what we mean by speed itself. If the connection between entangled particles is established instantaneously, faster than light, then what does that say about the nature of information and causality? Could there be a fundamental layer of reality where instant connections occur outside the framework of space-time? It's as if the universe has a secret shortcut, a non-local thread weaving through the cosmic fabric, unbound by the constraints that keep our everyday world orderly. But here's the catch. Despite these instant correlations, no usable information can be transmitted faster than light, because the results are fundamentally random. You can't send a message by simply measuring your particle and hoping your friend will know what you did on the other side. The non-locality revealed by Bell's tests doesn't allow for faster-than-light communication. Instead, it showcases that the universe's underlying quantum structure is woven with complex entanglement bonds that defy intuitive notions of distance and speed. Bell's experiments challenge the classical worldview, beautifully illustrating that our perception of a locally connected universe is incomplete. Instead, the quantum realm dances to a different tune, one where entanglement connects particles across the vast expanse of space with an effortless, instantaneous push that defies our everyday experiences of causality. It's like discovering that the universe is more like a vast interconnected web than a collection of isolated points. And this interconnectedness, these spooky actions at a distance, they're not just quirks of quantum mechanics, they hint at a deeper reality. A universe where the traditional speed limit applies strictly to objects moving through space, but where underlying threads of connection persist beyond the boundaries of speed, threading together the cosmos in ways we're just beginning to comprehend. It's a mind-bending idea, one that suggests the universe's most fundamental truths are woven into a tapestry far more intricate and mysterious than we ever imagined. Imagine sitting in a spaceship traveling through the cosmos at a significant fraction of the speed of light. Inside, everything feels normal. Clocks tick, rulers measure, movements seem natural. But outside your ship, the universe isn't so straightforward. That's where Einstein's idea of relativity comes in, showing that space and time aren't separate, independent entities, but are woven into a single, four-dimensional fabric called spacetime. Before Einstein, scientists viewed space and time as distinct absolute backgrounds, the stage for the universe. They believed events occurred at specific times regardless of where in space they happened. Einstein challenged this view by demonstrating that measurements of space and time depend on the observer's motion and gravitational influences. Imagine different observers on trains moving at various speeds. Each measures lengths and durations differently, but all measurements are correct in their own frame. The key is that what looks like a fixed universal clock or ruler is actually relative. Relativity teaches us that space and time are interconnected via the geometry of spacetime. When an object moves at high speed, its measurements of length and time are affected, lengths contract along the motion, and clocks tick more slowly from an outside perspective. These aren't quirks, but manifestations of the underlying spacetime structure. Think of spacetime as a flexible fabric that can curve and stretch. Its shape depends on the mass and energy within. Gravity, as Einstein redefined it, isn't a force pulling objects through space, but the curvature of the spacetime fabric itself. Massive objects like stars and black holes distort spacetime around them, creating curves that guide the motion of planets, light, and photons. When light passes near a massive object, it follows these curves, bending as Einstein predicted, a phenomenon confirmed during solar eclipses. Here, the curvature influences both space and time, intertwining their fates. Traveling at speeds close to light, your experience of space-time changes dramatically. Lengths in the direction of motion contract. Time for you seems normal, but a distant observer sees your clock slow down. These effects aren't just quirks. They are fundamental features of the space-time fabric itself, woven into its structure. Think of space-time as a dynamic four-dimensional foam, a complex landscape responding to mass, energy, and motion. Its geometry isn't flat and inert, it's malleable. Einstein's equations describe how mass and energy tell space-time how to curve, and that curvature guides how objects move, including light. It's a dance where space and time are inseparable partners, influencing and shaping each other constantly. This intertwining transforms our understanding of the universe. No longer do we see events occurring solely in space or in time. Each event occupies a specific point in the four-dimensional fabric, its position in both dimensions. Changes happen across this woven tapestry, emphasizing their unity. The unity of space and time also explains why the speed of light is the ultimate speed limit. Because information cannot surpass this speed, the structure of space-time ensures causality, preserving the order of cause and effect. The fabric prevents anything from outrunning light, weaving a universe where this constant is embedded in the very geometry of existence. Relativity reveals space and time as two sides of the same coin, inseparable, dynamic, and constantly reshaping each other. The universe isn't just a stage with separate parts. It's a seamless, four-dimensional mosaic where each event and particle connects through the curvature of space-time, forming a unified picture of reality that continues to surprise and inspire. Imagine zooming through space at speeds just shy of that universal speed limit, the speed of light. What happens to time and space around you when you're operating at such velocities? The universe reveals fascinating phenomena: time dilation and length contraction. Starting with time dilation. If you were on board a spaceship moving near light speed, from your perspective, everything would seem normal. Clocks tick, gears turn, nothing appears out of the ordinary. However, to an observer on Earth, your clock would seem to tick much more slowly. This isn't a quirk. It's embedded in the fabric of space-time, a consequence of Einstein's special relativity. The faster you go, the slower time appears to pass relative to someone stationary. If you travelled at near-light speed, decades could pass for your friends and family back home, while only a few years would go by for you. This effect is not just theoretical. It's been verified experimentally with atomic clocks on airplanes and satellites. This phenomenon challenges the idea of absolute unchanging time. Instead, time becomes intertwined with space, forming a space-time continuum that adapts to your velocity. As speed approaches light, the slowdown in time becomes more pronounced. It's like a cosmic time dilation switch that activates fully only near light speed. From your perspective, your journey feels normal, but to outside observers, it appears as if you're in slow motion. Next is length contraction, another astonishing effect. Consider a spaceship measured at rest, appearing elongated. From inside, nothing changes. The ship retains its normal length, but to an outside observer travelling near light speed, the ship appears significantly shorter along the line of motion. It's as if space itself is folding inward, squeezing the ship into a smaller silhouette. Length contraction only happens along the direction of travel. Dimensions perpendicular to the motion are unaffected. This contraction isn't just a visual effect, but rooted in the geometry of space-time. As velocity increases, distances in the direction of travel shrink to preserve the universal speed limit. Why? Because if objects could contract freely, it might be possible to exceed the speed of light, violating relativity. Length contraction ensures causality remains intact, cause and effect stay in order, by preventing any matter or information from surpassing the cosmic speed limit. Time dilation and length contraction are interconnected aspects of the same relativistic framework. When clocks slow down for objects travelling near light speed, their length along the path also contracts, maintaining the invariant speed of light in all reference frames. This synergy keeps the universe consistent and avoids paradoxes. Why does this matter beyond theory? Because it challenges classical ideas of absolute time and space. It reveals a universe where reality adapts and stretches at extreme velocities, where time flow is flexible and distances can contract. The cosmos becomes a pliable fabric, reshaped by motion, yet respecting an unbreakable universal speed limit. Understanding these effects benefits future space exploration, where near-light travel might someday be possible. It also deepens our grasp of the universe's history and fundamental laws, showing that reality is stranger and more beautiful than everyday experience suggests. It's a journey into the core principles governing everything, from fundamental particles to galaxies rushing through space at velocities nearing light speed. When we think about gravity, our minds often jump to the idea of objects falling or planets orbiting stars. But gravity's influence stretches far beyond just pulling things downward or holding planets in their orbits. It's woven into the very fabric of space-time itself. According to Einstein's theory of general relativity, gravity isn't a force acting at a distance as Newton imagined. Instead, it's the warping or curvature of space-time caused by mass and energy. Imagine space-time as a vast, flexible sheet. When a heavy object, like a star or a black hole, sits on this sheet, it causes a depression or a curve. Light travelling through this warped region doesn't follow a straight line in the traditional sense, but instead loops around or bends as it moves through these curved paths. This bending of light is what we observe as gravitational lensing, a cosmic magnifying glass in the universe, warping our view of distant galaxies and quasars. But how does this curvature influence the speed of light? Here's where it gets fascinating. In the realm of general relativity, the speed of light is locally always the same. That means that if you measure the speed of a beam of light in a small, freely falling laboratory, you'll find it moving at exactly the same speed, about 300 million meters per second, no matter where you are in the universe. This is a fundamental bedrock of physics. Locally, light's speed is invariant. However, the story becomes more nuanced when we look at larger scales or compare different regions of curved spacetime. To an observer watching from afar, light travelling through a gravitational field might appear to slow down or speed up. But this isn't a violation of the constancy of the speed of light. Instead, it's an effect of how spacetime curvature influences the measurement of space and time itself. Think of it like this. If you're in a moving car driving through a hilly landscape, your local speed feels constant to you, even if, from an external observer's perspective, the car appears to accelerate or decelerate because of the terrain. Similarly, the fabric of space-time affects how distances are measured and how time flows, leading to what appears as variations in the speed of light when viewed from different vantage points. Another intriguing aspect is gravitational time dilation, the phenomenon where time itself runs at different rates depending on the strength of the gravitational field. Near a massive object like a black hole, time ticks much more slowly compared to regions with weaker gravity. From an external observer's point of view, light escaping such a strong gravitational well is stretched out and appears redshifted. Its wavelength becomes longer, and it's as if the light is losing energy or slowing down, even though locally the light travels at the universal speed limit. This interplay between gravity, light and time weaves a complex yet beautifully consistent picture of our universe. In essence, the influence of gravitational fields on light's motion isn't about changing the fundamental speed of light itself. No matter how intense the gravity, locally light speed remains constant. But gravity does shape the path that light takes, bending it, and affecting its arrival time and energy as seen from different perspectives. This curvature of space-time guides light like a cosmic highway, with twists and turns, dictating how we see distant stars and the universe's overall structure. Ultimately, these effects remind us that light's journey through the cosmos is a dance choreographed by gravity's invisible hand. The speed limit remains unbreakable in a local sense, but the way light moves, bends and redshifts tells us a story about the universe's shape and the very fabric of reality itself. Exploring this dance reveals not just the limits of speed, but also the profound interconnectedness of space, time and gravity. An elegant tapestry that continually challenges our understanding of the universe's ultimate nature. Imagine the fabric of space-time as a vast, flexible sheet, an impression of the universe itself. When mass and energy are present, they don't merely sit passively on this sheet. They cause it to curve, creating the gravitational fields we experience as gravity. But what if we could do more than just let matter follow those curves? What if we could, in some way, actively manipulate space-time itself to leap across distances or carve shortcuts through the universe? This idea isn't just science fiction. It springs from the same principles we've been exploring: relativity, space-time curvature, and the fundamental limits imposed by the speed of light. The notion of warp drives and wormholes emerges from trying to find ways around the cosmic speed limit, the universal speed of light, which seems to serve as a sort of cosmic boundary. A warp drive, in its simplest conceptual form, involves contracting spacetime in front of a spacecraft and expanding it behind. Think of it like creating a bubble that moves through the universe faster than light could in a normal sense. Inside this bubble, the spacecraft could remain stationary relative to its local space-time. No faster than light travel, technically speaking. Instead, space-time itself takes the journey for us. It's as if we're surfing a wave rather than paddling through the water at impossible speeds. Now, at first glance, this idea seems to flirt dangerously with the laws of physics. After all, doesn't faster than light travel break causality, creating the possibility of time travel and paradoxes? That's where the deeper understanding of space-time and Einstein's equations comes into play. general relativity admits solutions that resemble these concepts, most famously the Einstein-Rosen bridge, or wormhole. This hypothetical tunnel connects two distant points in spacetime, potentially offering a shortcut across cosmic distances. But here's the twist. Sustaining such a wormhole or warp bubble isn't a simple matter. The equations demand exotic matter, substances with negative energy density, to keep the tunnel open or the bubble stable. Such exotic matter violates the normal energy conditions we see in everyday physics, and although its existence isn't outright impossible, it remains unproven. It's like trying to find an ingredient for a recipe that we've never observed in nature. Furthermore, the physics suggests that creating or stabilizing a wormhole might require enormous energies, possibly comparable to reversing the expansion of the universe itself. Even if theoretically possible, the practicalities stretch the bounds of current science and engineering to infinity. Scientists also explore whether the universe allows for these manipulations within quantum mechanics and relativistic constraints. Quantum field theory, for example, places limits on the types of energy fluctuations that could sustain a wormhole, and the question of whether such fluctuations could be harnessed remains open. Some researchers propose that the chaotic quantum foam at the Planck scale might seed tiny wormholes, but expanding these into usable shortcuts involves a leap of imagination and technology far beyond today's reach. Yet the allure remains. The idea that spacetime could be engineered, curved, warped, or tunneled resonates with our deep curiosity about the universe's nature. It pushes us to question the boundaries. Are the limits of light speed absolute, or are they merely the boundaries of our current understanding? Could spacetime itself hold the key to bypassing those limits, unlocking possibilities that currently seem impossible? Science fiction has often depicted warp drives and wormholes, fueling our dreams of interstellar travel. But beneath these stories lies a foundation rooted in profound physics. The curvature of spacetime governed by Einstein's equations, the peculiarities of quantum mechanics, and the mysterious nature of exotic matter. While we're not at the point of building warp engines or wormholes, yet the exploration of these ideas continues to stretch our thinking, hinting that the universe might be more flexible and strange than we dare to imagine. Feynman's interpretations of spacetime sent ripples through the way we understand the universe, like a thunderclap awakening us from a long-held dream. He didn't just accept the fabric of spacetime as a static stage where particles move and interact. He hinted at something far more dynamic, something that breathes and evolves with the universe itself. His insights helped peel back the layers of mystery surrounding this cosmic fabric, revealing that spacetime is not just a backdrop, but a living, breathing entity deeply intertwined with the very essence of reality. Through Feynman's lens, we see that spacetime isn't simply curved by mass or energy. It's influenced by the dance of quantum fields, the flickering vibrations of particles, and the flow of information. It's as if spacetime responds to the whispers of particles darting through the quantum realm, giving rise to the phenomena we observe: gravity, causality, and even the nature of time itself. One of the most eye-opening revelations Feynman brought into focus stems from his interpretation of quantum electrodynamics, the theory that describes how light interacts with matter. Instead of picturing particles like electrons just moving along straight paths, Feynman's diagrams introduced the idea that these particles perform a kind of cosmic dance, exploring all possible routes simultaneously. Every potential journey, no matter how strange, contributes to the outcome. These paths through space-time, are not just mathematical abstractions, they are fundamental to the universe's fabric. They reveal that space-time isn't a rigid scaffold, but a dynamic web, woven from countless quantum possibilities. This perspective challenges our classical instincts. We think of space-time as fixed and absolute, a smooth continuum stretching from the Big Bang to the distant future. Feynman's approach, however, paints it as a probabilistic playground, an arena where particles and waves create a tapestry of potentialities. It suggests space-time itself is shaped by these quantum interactions, adapting and fluctuating at unimaginably tiny scales. In this view, the very geometry of space-time is not static but emergent, arising from the tangled quantum field interactions that Feynman's diagrams so brilliantly illustrate. Feynman's interpretation reveals something profound about the unity of physics. It shows that the seemingly separate worlds of classical space-time and the quantum realm are chapters of a single story, an intricate, interconnected narrative. Space-time in this light isn't separate from particles or forces. It's an extension of their collective behavior. Every quantum event, every exchange of a photon, subtly rewires the fabric of spacetime. It's a feedback loop. Particles influence spacetime, and spacetime influences particles in a cosmic ballet that's far from static. This dynamic view also lends new insight into causality. If spacetime is shaped by quantum interactions, then causal relationships are more than simple cause and effect sequences. They are woven into the very structure of reality at the quantum level. This means that what happens in one corner of the universe is subtly connected to what unfolds elsewhere, not just through classical signals moving at light speed, but through an underlying quantum web that knits everything together. Feynman's interpretations open a doorway to understanding the universe as an interconnected, evolving entity, where space-time and quantum fields form a unified whole. It's a universe that's constantly in flux, a cosmic fabric shimmering with possibilities, woven from the fundamental dance of particles and waves. And in this dance, we glimpse the true nature of space-time, not just as the stage of reality, but as an active participant in the unfolding story of existence. The idea of surpassing the speed of light has long fascinated scientists and science fiction fans alike, but can Einstein's theories actually allow for faster-than-light travel? This question pushes the boundaries of our understanding of physics, and the answer is nuanced. Within Einstein's special relativity, the speed of light isn't just a high-speed limit, it's embedded into the fabric of reality. As objects accelerate closer to light speed, their relativistic mass effectively increases, requiring more energy to go faster. Approaching light speed demands infinite energy, making it impossible for any object with mass to reach or exceed that barrier. This isn't a technicality, it's a fundamental aspect of how space-time and energy are intertwined in Einstein's equations. In this framework, faster-than-light travel seems off-limits. Anything attempting to break this barrier faces insurmountable energy requirements, and causality, the cause and effect chain that holds our universe together, would break down. Travelling faster than light would mean effects could precede their causes, creating paradoxes like time travel into the past, threatening the consistency of physical law as we understand it. However, the universe has surprises, and physicists have explored theoretical loopholes that seem to skirt these limits. One compelling idea is wormholes, hypothetical tunnels through space-time connecting distant regions of the universe. Think of space-time as a vast, wrinkled fabric. A wormhole could be akin to a shortcut bridging 2 points, allowing travel faster than light between them. Yet, creating and stabilizing a wormhole would require exotic matter with negative energy density, something never observed and possibly impossible to produce in the needed quantities. Even if such matter exists, manipulating space-time on this scale is beyond current technology and might threaten the universe's stability. Another idea involves warp drives, like the Alcubierre drive. This concept involves expanding space-time behind a spacecraft while contracting it in front, creating a bubble that moves faster than light relative to external space. Inside this bubble, the spaceship remains at sublight speeds, sidestepping relativistic limits. The problem? It would need enormous amounts of negative energy and exotic matter, details still purely theoretical. While Einstein's equations permit such ideas mathematically, their practicality faces astronomical hurdles, leaving them speculative. Some physicists have pondered tachyons, hypothetical particles that always travel faster than light. If they existed, tachyons could violate causality, transmitting information backward in time and creating paradoxes. Since no experimental evidence supports their existence, they remain speculative curiosities. Ultimately, within Einstein's framework, faster-than-light travel seems impossible for objects with mass. It would require rewriting fundamental principles of causality and energy. Yet, the universe isn't limited by current understanding. Concepts like wormholes and warp drives challenge these limitations, pushing the boundaries of physics and prompting questions about the true nature of reality. These ideas suggest that Einstein's restrictions are based on our current knowledge, but the universe might hold secrets that could someday make the impossible feasible, or that our theories need to evolve. The pursuit continues. The question isn't only whether faster-than-light travel could happen, but what such possibilities reveal about the universe's fabric. Each discovery brings us closer to understanding whether Einstein's limits are absolute or simply the frontiers of what we currently understand. As we explore deeper into space and physics, our grasp of reality expands, and the line between what's possible and impossible blurs. The quest to understand the cosmos continues, driven by curiosity and the desire to uncover what lies beyond the known laws of physics. 544 words total. Let's explore why objects with mass can never reach the speed of light from a mathematical perspective. This stems from Einstein's special relativity, which redefined motion and energy at high speeds. Imagine accelerating a spaceship. Initially, it's like pushing a car uphill. The faster you go, the more force you need. But as you increase speed, something extraordinary happens mathematically. To understand this more intuitively, think of pushing a ball uphill that gets steeper and steeper. Initially, effort is manageable, but as you near the top, it becomes almost vertical. To reach the summit, you'd need infinite effort. Similarly, as an object accelerates toward mce, its effective inertia, the resistance to further acceleration, increases without bound because of relativistic mass increase. It's tempting to think we could reach mce by adding enough energy, but the math shows otherwise. The fabric of spacetime and the governing equations reveal the speed of light as an insurmountable boundary for mass-bearing objects. The barrier isn't merely practical, it's fundamental, woven into the equations that describe our universe. Mass increase with velocity is a common misconception. Modern physics clarifies that what actually increases are relativistic momentum and energy, not rest mass. Rest mass remains constant, an intrinsic property of matter. The rising energy demand results from the way spacetime responds to speed, ensuring causality and order are preserved. Massless particles like photons, which have no rest mass, always travel at c. They aren't limited by the infinite energy barrier because their energy relates directly to momentum via PC. They don't need to overcome increasing inertia. Their existence depends on moving at light speed, the cosmic speed limit. In essence, the mathematical reason objects with mass cannot reach mce is rooted in how relativistic momentum and energy become infinite as we approach that boundary. The equations aren't abstract. They reflect fundamental truths about the universe's structure. The cosmic speed limit is not just a number, but a fundamental boundary embedded in the very fabric of space-time. Imagine a spaceship trying to push past the universe's speed limit. As it accelerates, something strange occurs, something that challenges our intuition about motion and reveals the deep structure of reality. The closer the vessel gets to light speed, the more it must fight against an invisible barrier, the fabric of space-time itself. At low speeds, adding energy to an object feels simple. You activate a rocket thruster, and it speeds up. The energy you input directly increases the object's velocity. More speed means more energy. But as the velocity approaches light speed, the situation becomes extraordinary. The energy you supply doesn't just make the object go faster, it begins to change its very nature. The key is Einstein's famous equation, equals mc squared. Total energy of an object relates to its mass, and the speed of light. Chaos. As the object accelerates, its energy increases but not linearly. Instead, the energy grows exponentially as the velocity nears light speed. To understand this, consider relativistic mass, or more accurately, relativistic momentum. The closer an object gets to light speed, the more its inertia, its resistance to further acceleration, increases dramatically. This is because, according to special relativity, the object's effective mass depends on its velocity. Mathematically, this dependence is expressed through the Lorentz factor, denoted by gamma g. This gamma factor blows up as speed approaches light speed. At everyday speeds, gamma is nearly 1, and classical Newtonian physics suffices. But as the vessel approaches 200,000 miles per second, the speed of light skyrockets. At half the speed of light, g is about 1.15. At 95% of light speed, roughly 3, nearing 99%, or exceeds 20. Near the speed of light, g tends to infinity. What does this mean for energy? The relativistic kinetic energy is given by ek joule, g, 1, m, c squared. As g increases, the energy needed to accelerate the object climbs without limit. Pushing a spaceship from 99% to 99.9% of light speed demands vastly more energy than reaching 99%. The energy jump becomes enormous, approaching infinity as the speed nears light itself. Why does it take so much energy? In relativistic physics, mass and energy are two sides of the same coin. As the ship accelerates, g increases, and the ship's relativistic mass, or more precisely its resistance to acceleration, approaches infinity. Think of trying to push an object that expands endlessly. No matter how powerful your engines, it requires a disproportionate amount of energy for even a tiny increase in speed. This isn't just a math curiosity. It's a fundamental aspect of the universe's structure. The speed of light acts as a cosmic speed limit because accelerating an object toward it would require infinite energy. If finite energy could achieve this, objects might surpass it. Violating causality and distorting spacetime's fabric, the universe enforces this barrier through its geometry and the invariance of the speed of light. This exponential rise in energy explains why nothing with mass can reach or exceed light speed. The barrier isn't merely technological, it's built into the cosmos's principles. It influences how matter and energy interact, impacts particle behavior at quantum scales, and governs cosmic evolution. Thinking about this reveals a poetic truth: how the universe set an ultimate speed limit because of the intertwined nature of energy and mass. It designed it so that achieving superluminal travel would require infinite energy, preserving causality and the chain of cause and effect in the universe. Every time we hear about mass approaching light speed, remember, the closer it gets, the more energy it must consume, exponentially more. It's like trying to push a boulder up an infinitely steep hill that rises toward the stars. You can get close, but you can never reach the top. This restraint reflects the elegant order of the cosmos, an eternal testament to its profound, beautiful structure. Pushing an object to reach the speed of light isn't just a matter of accelerating a little more. It's like trying to push a mass through a barrier that keeps shifting and growing more formidable the closer you get. The closer an object gets to the speed of light, the more its relativistic mass, or more accurately its effective inertia, increases without bound. As speed nears that universal limit, the energy required to keep accelerating it climbs exponentially, spiraling towards infinity. That means, theoretically, achieving or surpassing the speed of light would demand an infinite amount of energy. But what does this really mean for our universe and its fundamental laws? For starters, it suggests that light speed is a hard cosmic barrier. An energy wall no amount of fuel or force can breach. Is not just an arbitrary speed limit, but a fundamental feature woven into the fabric of reality. Imagine trying to push a car up a hill that grows steeper the more you push, until, eventually, it becomes impossible to get to the top without infinite effort. That's the universe's way of telling us, you can approach me, but never surpass me. This infinite energy demand acts like an unbreakable barrier, safeguarding causality, the principle that cause precedes effect, and ensuring that information cannot travel faster than light. If it were somehow possible to reach that speed, objects would undergo bizarre and extreme transformations. Their mass would grow limitless, and so would the energy needed. The formula E equals mc squared, which relates energy to mass and speed, reveals this elegantly. As velocity approaches the speed of light, the Lorentz factor, which governs how quantities like length and time are altered, tends towards infinity. This means the object's relativistic mass would become infinite, and to push it further, you'd need an infinite supply of energy. Practically, it's like trying to fill an infinitely deep well with a finite amount of water, impossible by the very laws of physics. But what happens if you could somehow fuel such an infinite energy demand? The universe would likely break down in chaos. Transcending the speed of light would violate causality, allowing for scenarios where effects could precede causes. It would unleash all sorts of paradoxes: time travel, information moving backward, and a breakdown of the fundamental sequence of events that holds reality together. This is why physics, as we understand it, treats the speed of light as an insurmountable boundary, an unchangeable feature of the universe's structure. The energy implications shed light on why nothing with mass can ever catch or reach the speed of light. It's not just a practical limitation, but a fundamental rule encoded into the very equations that govern spacetime. No matter how advanced our technology gets, or how much we manipulate energy, we will forever remain bound to the realm where light travels at that relentless, unbreakable speed. The infinite energy demand is more than a technical hurdle. It's a deep signal from the universe that the cosmos is built with constraints that preserve its order. It's a cosmic safeguard against chaos, ensuring that causality remains intact and the universe's history remains consistent. In a universe where reaching the speed of light demanded infinite energy, the very fabric of reality would seem almost sacred in its inviolate nature, preventing us from breaking the most fundamental cosmic laws. And this is the mystery and beauty of it. The impossibility of surpassing light serves as a profound reminder that, at the universe's core, some limits are fundamental. They are the guardrails that preserve the orderly, interconnected cosmos we observe, limits that are, in the end, a testament to the universe's coherence and its grand design. Imagine racing down a highway where the speed limit is not just a suggestion, but the very fabric of the universe's boundaries. This is the essence of how the concept of relativistic mass shapes our understanding of the universal speed limit, light speed. When we first learn about motion, we think in terms of speeds increasing without bound, feeling like a rocket could, in theory, keep accelerating forever. But in the world of Einstein's relativity, things aren't so simple. As an object accelerates closer and closer to the speed of light, its relativistic mass begins to increase dramatically, acting like an invisible brake that makes further acceleration more and more difficult. Relativistic mass isn't mass in the traditional sense we think of in everyday life. Instead, it's a way of describing how an object's resistance to acceleration grows as it approaches light speed. When an object moves faster, it carries more energy, and because energy and mass are equivalent, thanks to Einstein's famous equation, E equals m², the object acts as if it's getting heavier. But it's crucial to see that this mass isn't a static property of the object itself. It's a way to understand how the object's inertia reacts to forces at relativistic speeds. Now, why does this matter in understanding the speed limit? Because it effectively makes reaching or surpassing the speed of light impossible for anything with mass. To go faster, you'd need to add more and more energy, but each increment results in a disproportionately larger increase in the object's relativistic mass. As the speed tips toward the speed of light, your energy input doesn't produce much more speed. It's like trying to push a boulder uphill that gets heavier and heavier the faster you push it. The energy required to reach light speed approaches infinity. That boundary, that infinite energy barrier, is embedded into the fabric of spacetime itself. This isn't just a theoretical quibble, it's a fundamental principle woven into how the universe operates. The idea of relativistic mass highlights that mass and energy aren't just interchangeable, but are part of a universe where speed itself is constrained. Nothing with mass can reach light speed, because doing so would require an infinite amount of energy, a feat so impossible that the universe prevents it from ever happening. This concept also reshapes our intuitive notions about motion. Instead of objects simply moving faster with more force, their very resistance to acceleration becomes more pronounced as they near light speed. Imagine trying to push a car that gets physically heavier the faster you go. Your efforts would never guarantee crossing that cosmic threshold. Relativistic mass underscores that the speed of light isn't just a speed limit for photons, it's a fundamental boundary more profound. It acts as a cosmic speed bump, a limit rooted in the very structure of space-time and energy. This is why, no matter how much energy you pour into a spaceship, it can never catch up to this universal speed cap with a mass in tow. The universe's rules, as bizarre and counterintuitive as they may seem, prevent such crossing from happening. In essence, the idea of relativistic mass provides a vivid, almost visceral way to understand why the universe keeps its speed limit fixed at the speed of light. It's not just a rule, it's a consequence of the incredible power of Einstein's insight: space, time, energy and mass dancing together in a delicate balance that forbids anything with mass from surpassing that breathtaking cosmic boundary. That boundary is not just a number, it's a reflection of the universe's deepest truths, limitless in potential, but bounded by the very fabric that makes reality possible. Imagine a world where we could bend the universe itself, creating pathways through space that seem to slide faster than light, without actually breaking the cosmic speed limit. That's the tantalizing promise of warp drives, a concept rooted deeply in Einstein's theory of relativity, but stretching its boundaries into the realm of science fiction. Yet, in doing so, they reveal profound truths about the nature of the universe's speed limit and how far our understanding of physics can push into the unknown. Warp drives, at their core, hinge on the idea of manipulating space-time rather than travelling through it in the conventional sense. Instead of an object speeding through the universe, the concept involves contracting space in front of a spacecraft and expanding it behind. Think of it like a ripple in a pond. Rather than moving the boat forward through the water, you create a wave that carries the boat along without it actually exceeding the usual speed limit of the ripples. In theory, this allows for faster-than-light travel, without violating the cosmic speed limit because the spacecraft itself isn't moving faster than light relative to the space-time immediately around it. Instead, the fabric of space-time is doing the heavy lifting. This idea challenges our understanding of limits because it hints that the ultimate speed, light speed, isn't an absolute barrier in the traditional sense. Instead, it might be a boundary for objects moving through spacetime, but not for spacetime itself. If you can manipulate spacetime geometry, then perhaps there's a way to navigate the universe beyond the restrictions that seem so fundamental today. This is what makes warp drive such a compelling hypothetical. By curving space rather than flying through it, we're rethinking what speed really means. However, these notions aren't just fanciful dreams, they confront some of the deepest problems in physics. For example, creating a warp bubble would require exotic matter with negative energy density, a substance that doesn't behave like the matter we're used to and has only been theorized so far. Its existence is uncertain, and the energy requirements for such a device would be astronomical, possibly greater than the total energy content of our galaxy. Still, the very idea opens up questions about the fabric of space-time and the possible flexibility of the universe's underlying structure. Beyond the technical hurdles, warp drives reveal a fundamental insight. The speed of light isn't simply an obstacle, but a feature woven into the fabric of space-time itself. It's a limit that emerges from the geometry of the universe, from how energy and matter influence the curvature of space-time. Yet, this limit also hints at hidden layers of reality, layers where the rules we know might not apply if we can manipulate the geometry at a profound level. Thinking about such scenarios invites us to see the universe as more than just a vast inert stage. It's a malleable, dynamic tapestry that responds to the rules we discover and possibly to the rules we learn to change. Theories like warp drive serve as a scientific compass, pointing us toward a richer understanding of what's possible, and hinting that the universe's speed limit, while seeming absolute, might be more flexible than we ever thought, waiting for us to unlock the secrets of spacetime's true potential. Imagine pushing the boundaries of travel and communication, aiming to surpass the cosmic speed limit. Light speed itself, it's a captivating dream. For centuries, humans have gazed at the stars, wondering if we could someday traverse the galaxy or communicate instantly across space. But the universe has rules, and the speed of light is its ultimate boundary. These constraints aren't just numbers or equations, they serve to preserve causality and the flow of time. When considering faster-than-light travel, current physics break down. Special relativity states that as objects approach light speed, their mass effectively becomes infinite, requiring infinite energy to go further. It's like trying to run faster, but needing more effort with each step until exhaustion. This makes reaching or exceeding light speed impossible with finite resources. Can we bend or warp space-time? Sci-fi depicts warp drives and wormholes, shortcuts through space-time, concepts rooted in Einstein's equations. However, such ideas face constraints. Stabilizing these phenomena often requires negative energy, or exotic matter that seems unphysical. These materials appear non-existent in nature. Although mathematically intriguing, such concepts are hypothetical because they conflict with known physics. Creating a bubble for faster-than-light travel might demand conditions that break conservation laws or involve energy densities beyond what the universe permits. Quantum physics complicates matters further. Quantum entanglement allows for instant correlations, spooky action at a distance, where entangled particles influence each other faster than light. Yet, these correlations cannot be used to send information faster than light. They're akin to a secret handshake that only makes sense when compared later, thus not enabling faster-than-light messaging. This fundamental limit preserves causality. No faster-than-light communication exists at the quantum level. For faster spacecraft, these principles suggest reconsidering what faster means. Instead of trying to defy the light speed barrier, considered impossible, we explore alternatives, high-energy propulsion like nuclear thermal engines or ion drives that bring us closer to neighboring planets. Concepts such as solar sails harness sunlight's momentum to drift through the solar system without fuel. Relativistic spacecraft, small probes traveling near light speed, are under study, pushing propulsion technology as far as possible, even if surpassing light remains unreachable. In communication, these constraints mean working within universe-imposed limits. Light remains the fastest messenger. Faster methods confront fundamental barriers. Quantum entanglement might create the illusion of instant communication, but it can't be used to send messages faster than light. Instead, researchers aim to optimize existing methods, improving signal efficiency or developing quantum repeaters to extend communication ranges, without violating physical laws. All these constraints shape ambitions but also foster ingenuity. They compel us to seek understanding rather than breaking barriers. The universe's unwavering speed limit isn't merely a barrier, it guides us toward deeper questions and new solutions. Instead of rushing to surpass the light barrier, perhaps our goal is to unravel spacetime itself, discovering new rules, and maybe working within them in ways we haven't yet imagined. Rather than solely focusing on exceeding light speed, these constraints inspire innovation within the universe's parameters. Exploring high-energy propulsion, possible spacetime manipulation, and optimized communication methods deepens our understanding of the cosmos. These limits challenge us to think more creatively, leading to revolutionary ideas. They prompt questions about reality, causality, and the nature of spacetime itself. The universe's speed limit shapes ambitions but also broadens horizons. Rather than viewing constraints as barriers, they motivate us to explore new physics, develop advanced technologies, and deepen our grasp of reality. The quest to reach the stars or communicate across vast distances is bounded by these laws, but perhaps they hold the key to greater discoveries. The challenge isn't just outpacing light, but comprehending the universe more fully. Ultimately, these constraints act less as roadblocks and more as invitations, calls to decipher the universe's underlying fabric. Each limitation pushes us to evolve and imagine new possibilities, crafting solutions that operate within the universe's laws. Our pursuit isn't solely to break barriers, but to understand the fundamental nature of reality, and maybe learn how to dance within it, to find novel ways to explore, communicate, and thrive in a cosmos governed by unbreakable laws. The idea of tachyons has fascinated people for decades, sparking imaginations about what might lie beyond current physics. These hypothetical particles are said to travel faster than light, and, if they existed, could revolutionize our understanding of causality, communication, and spacetime itself. But is there any real basis for tachyons? And what would their properties be? Let's explore that. Tachyons originate from special relativity equations, which permit particles with imaginary mass, a mathematical oddity suggesting they exist only in theory. Normal particles with real, positive mass, like electrons or protons, move at speeds less than light, and as they accelerate toward it, their energy requirements increase infinitely. This prevents them from reaching or surpassing light speed. Tachyons are theorized to have imaginary mass, meaning their mass squared is negative. This implies that as they gain energy, they would slow down, approaching the speed of light from above. Conversely, losing energy would make them go faster, even infinitely fast. They are imagined as the cosmic speedsters who never slow down below light speed. Practically, if tachyons existed, they would possess mind-bending properties. Traveling faster than light, they could appear to violate causality. Signals or effects might arrive before their causes, opening paradoxes like the grandfather paradox. Sending information back in time could threaten the cause and effect structure of our universe, leading to logical contradictions. Another key property is that their energy diminishes as their speed increases, approaching zero as their velocity reaches infinity. This counterintuitive trait means they require less energy the faster they go, opposite to ordinary particles. This makes tachyons extremely unstable and difficult to detect, as they wouldn't interact with matter in ways allowing observation. They could exist in a quantum haze, flickering at the edges of detection, never manifesting openly. Scientists have debated whether tachyons could be more than mathematical curiosities. Some have speculated they might relate to neutrinos, particles with tiny, possibly imaginary mass components, though current measurements suggest neutrinos travel just below light speed, not faster. Others believe tachyons could be part of phenomena in higher dimensions, or exotica from string theory or models aiming to unify gravity and quantum mechanics. Despite their allure, no experimental evidence confirms tachyon existence. Observations from telescopes, particle accelerators, and quantum experiments strongly support the idea that nothing with rest mass surpasses the speed of light. If tachyons did exist, their weak interactions and weird properties suggest they'd be tough to detect, or even to exist within classical physics. Some physicists suggest tachyons might only exist as virtual particles within quantum fields. These brief entities could influence other particles through quantum fluctuations, subtly affecting phenomena like quantum tunneling or the Casimir effect. But that wouldn't imply they travel faster than light causally. Instead, they'd be part of the quantum background, popping in and out without violating established laws. Speculative ideas also connect tachyons to the structure of spacetime. Some theories suggest the universe's speed limit results from its geometry and topology. In higher dimensional models, faster-than-light travel might be possible via shortcuts like wormholes, connecting distant points without involving tachyons directly. These pathways could permit superluminal travel or communication, avoiding causality violations and paradoxes associated with tachyonic particles. Ultimately, whether tachyons are possible hinges on our understanding of physics' limits. They are elegant mathematical constructs that challenge notions of causality, but haven't been observed or confirmed as real particles. The universe's consistent behavior, obeying the light speed limit, suggests that if tachyons exist, they operate in realms beyond current reach, perhaps confined to quantum fields or higher dimensional spacetime. The concept stirs the imagination, stories of faster-than-light communication and time travel. Yet, it remains a fascinating hypothesis, highlighting the mysteries surrounding the universe's speed limit. The search continues, and perhaps someday, through new physics or discoveries, the veil will lift to reveal whether these elusive speedsters are just ideas or true aspects of reality. Quantum tunneling is a phenomenon that often surprises even seasoned physicists. Imagine a tiny particle, like an electron, approaching a barrier it seemingly shouldn't cross because it lacks enough energy. Classical physics says that without sufficient energy, the particle is stuck on one side. But quantum mechanics introduces the possibility that the particle can be found beyond the barrier, despite classical rules forbidding it. This process, called quantum tunneling, is essential in many natural and technological phenomena, such as nuclear fusion in the sun, tunneling microscopes, and radioactive decay. What's intriguing is how it challenges our intuition about cause and effect, especially regarding the speed of tunneling. Some wonder, does tunneling occur faster than light? Could it be a form of superluminal transfer? The answer isn't straightforward. To understand this, we need to clarify what tunneling involves and what it doesn't. Tunneling concerns probabilities and wave functions. A wave function describes the likelihood of finding a particle in a specific place. When an electron encounters a barrier, its wave function doesn't abruptly stop but extends into and beyond the barrier. This extension means there's a finite probability for the electron to appear on the other side, even if classical physics suggests otherwise. What draws attention is the idea that the tunneling time, the duration it takes to tunnel, sometimes appears extremely short, even suggesting faster than light transfer. Experiments measuring tunneling times have found instances where it seems shorter than the time light takes to cross the same distance. This spurs speculation. Is tunneling a form of superluminal transfer? However, the key point is that while some measurements imply an effective speed exceeding light, this doesn't mean any information or matter is traveling faster than the universe's speed limit. Physical laws, especially relativity, prohibit faster than light transfer of information or energy, because that would break causality, the cause and effect chain underpinning our universe. In essence, the apparent superluminal nature of tunneling reflects quantum interference effects and the behavior of probability amplitudes, not actual particles or signals traveling faster than light. Tunneling is probabilistic. It doesn't enable faster than light communication or influence. It's more like a shortcut in the quantum landscape, an almost mysterious crossing that doesn't break energy conservation or causality. Think of it as a hiker finding a hidden pass through mountains. They still travel from point A to B, but the route isn't a straight line, and they aren't defying the speed limit. This analogy underscores that quantum tunneling isn't about breaking fundamental laws, but about how wave functions behave under quantum rules. Physicists carefully differentiate between the appearance of superluminal effects and actual superluminal communication. The faster-than-light impression arises from quantum interference and non-local wave function effects, not from particles or signals traveling faster than light. Phenomena like wave function collapse or entanglement seem instantaneous, hinting at faster-than-light connections, but these don't transmit usable information or violate relativity. If tunneling allowed faster-than-light signaling, it would create paradoxes, such as sending messages into the past, undermining causality. The universe maintains its speed limit through various mechanisms, allowing quantum peculiarities to occur without breaching the fundamental rule. Nothing with mass or information can surpass light speed. Quantum tunneling embodies the strange, probabilistic, boundary-exploring aspects of quantum physics. Particles can appear where they shouldn't, doing things that challenge classical intuition. Despite its rapid appearance and implications of faster-than-light effects, tunneling does not serve as a loophole for breaking Einstein's cosmic speed limit. Instead, it illustrates how the quantum world operates in ways that are often counterintuitive. It highlights that what seems like superluminal transfer is really about the behavior of wave functions rather than particles or information moving faster than light. The quantum universe's rules are subtle and non-intuitive. They permit phenomena that appear to challenge known physics but do not violate it. While quantum tunneling might seem to be a loophole, it isn't. It demonstrates the strange and wondrous nature of the microscopic universe, one where faster than light doesn't necessarily mean breaking the rules, but reflects our incomplete understanding. In conclusion, quantum tunneling challenges classical notions of speed but ultimately respects the universal speed limit. It's a manifestation of quantum probability and wave function behavior, an exotic but lawful aspect of the quantum realm. The superluminal appearance is more about the peculiarities of quantum mechanics than actual violation of causality or relativity. Imagine the impossible becoming possible, bending and stretching space-time itself to create shortcuts across cosmic distances, or travel faster than light. Wormholes and warp drives are theoretical ideas pushing physics beyond current limits, offering glimpses into potential future advancements and our understanding of the universe. Wormholes, also called Einstein-Rosen bridges, are hypothetical tunnels through space-time. Think of a sheet of paper with 2 points marked at opposite ends. Normally, travelling between these points involves crossing the entire sheet. But if the paper is folded so the 2 points touch, a shortcut, or wormhole, is created, allowing near-instantaneous connection between distant parts of the universe. Theoretically, spacecraft could use wormholes to leap vast cosmic distances quickly, making interstellar travel feasible, which might otherwise take tens of thousands of years at light speed. The challenge is whether such wormholes could naturally exist or be artificially created. Current physics suggests stable, traversable wormholes would require exotic matter, substances with negative energy density, that has yet to be observed in known forms. This exotic matter would act as an anti-gravity agent, preventing the wormhole from collapsing. Without it, the wormhole would close instantly, crushing anything inside. Even if exotic matter exists, maintaining a stable wormhole might demand energies far beyond current or foreseeable technology, perhaps impossible to achieve. Similarly, warp drives are speculative, but captivating concepts. Popularized by science fiction like Star Trek, a warp drive would contract space in front of a spaceship and expand it behind, effectively moving faster than light without violating physics laws. Instead of moving through space faster than light, the ship remains stationary inside a distorted region of spacetime that moves forward, making it appear to travel faster than light. This creates the illusion of superluminal velocity. The most famous theoretical model is the Alcubierre drive, which relies on exotic matter, negative energy density to create a warp bubble. This bubble would distort space similarly to a wave on a pond, propelling the ship faster than light without breaking relativity. Yet again, exotic matter remains hypothetical. Moreover, the energy needed to sustain such a bubble could reach astronomical levels, possibly equivalent to the mass energy of a planet or star. While promising, developing such a drive might be centuries or millennia away. Still, these ideas inspire reconsideration of the limits of space travel and fundamental physics. The implications of wormholes and warp drives extend well beyond science fiction. If feasible, they would revolutionize physics and our understanding of the universe. Humanity could undertake interstellar or even intergalactic travel, opening unprecedented horizons for exploration. Entire civilizations might connect across galaxies, facilitating travel, communication, commerce, and cultural exchange on an unimaginable scale. The focus then shifts from understanding the mathematics to developing the technology and energy sources necessary to harness these phenomena. However, these concepts also compel us to question the nature of reality itself. Do wormholes exist naturally, perhaps as remnants from the universe's early moments, waiting to be discovered? Are they stable enough for passage, or are they illusions? Could we someday engineer a stable wormhole or warp bubble if we can understand exotic matter fully? These questions stir the imagination and motivate ongoing research into the universe's fundamental laws. They challenge the boundaries between scientific possibility and science fiction. These ideas also threaten to alter Einstein's theories, suggesting that special and general relativity might not be the entire story. If such constructs are possible, they could dramatically influence notions of causality, raising philosophical debates about time travel and the nature of reality, topics long explored by scientists and thinkers alike. The broader significance is profound. These theories offer a glimpse of a future where the universe's mysteries may be within reach, if we learn to unlock the secrets of exotic matter, energy manipulation, and space-time engineering. For now, they symbolize human curiosity and imagination, encouraging us to look to the stars and wonder whether perceived limits are fixed or stepping stones towards something greater. They remind us that the universe may be more flexible and wondrous than current understanding suggests, waiting to be unlocked by future discoveries. In summary, wormholes and warp drives are speculative yet fascinating concepts that could revolutionize space travel, physics, and our grasp of reality. Achieving them remains a distant goal due to enormous technological and energy challenges. Nevertheless, they continue to inspire scientific inquiry and philosophical reflection. Whether these ideas become reality or remain theoretical, they push us to think beyond current limitations, fueling curiosity about the universe's deepest mysteries. They compel us to consider a universe more adaptable and wondrous than what we currently comprehend, waiting for future breakthroughs to unlock its secrets. Ideas like warp drives or wormholes often seem like shortcuts, ways to beat the universe's speed limit. But do they truly break the rules? Or are they just challenging our understanding? The speed of light isn't just a number, it's woven into the fabric of reality. It acts as the cosmic speed limit, the boundary beyond which nothing with mass can go. Einstein's relativity shows that, as an object with mass accelerates toward light speed, its energy requirements approach infinity. To reach or surpass that speed would require infinite energy, impossible within current physics. This limit is rooted in causality, the idea that cause precedes effect. If something travelled faster than light, effects could happen before causes, creating paradoxes and undermining reality's logical structure. The universe relies on this speed limit to prevent chaos. However, science fiction and some advanced theories suggest bending or bypassing this rule. Do they really? It depends on interpretation. Many proposals, like warp drives or wormholes, don't outright violate the universe's laws but imply our understanding is incomplete. They suggest that the rules apply locally, not universally. For example, a warp drive, popularized in sci-fi and based on real physics, manipulates space-time rather than objects moving faster than light within space. It contracts space-time in front of a craft and expands it behind. The ship remains stationary locally, but the space around it moves faster than light. This idea stems from Einstein's general relativity, but requires exotic matter with negative energy to stabilize the warp bubble, substances we've yet to observe. Wormholes are like tunnels connecting distant points. They don't involve objects moving faster than light through normal space, but instead bend space-time to connect two points directly. These structures don't violate Einstein's laws, they utilize permitted solutions, but they're not yet practical or confirmed. Quantum phenomena, like entanglement, seem to send signals instantly over vast distances. Does that violate the speed limit? Not quite. Entanglement involves correlated states established faster than light could carry information, but it doesn't enable faster than light communication. Usable information transfer still respects the universal speed limit, preserving causality. These ideas more challenge our understanding than break laws. They stretch the framework of physics, prompting scientists to refine theories or seek entirely new physics. It's similar to a puzzle. Each new idea, be it wormholes or warp bubbles, does not necessarily break the universe's rules, but suggests hidden corridors and dimensions we're only beginning to explore. Consider the universe as a complex clockwork, bound by gears and springs. Sometimes, phenomena seem to outpace the speed limit because we misinterpret how the gears work. Perhaps the gears aren't directly moving faster, they're moved by something else, or maybe the laws are more flexible than they appear. So do these concepts violate the speed limit? Not exactly. Instead, they challenge what we believe is possible within that limit. They push us to expand theories, to envisage a universe where the limit is a frontier rather than a wall, a boundary of the known, awaiting exploration through new physics, ideas, and tools. It's a reminder that the universe is mysterious. Just because something seems impossible today doesn't mean it always will be. Scientific understanding is constantly evolving, and what appears to break the rules now might become a key to deeper truths tomorrow. These ideas encourage us to see the universe as more flexible and complex than we imagine. They push us to question the fundamental limits and open the door to new possibilities. The universe may well have hidden corridors and dimensions as yet undiscovered that could change everything we think about speed, space, and reality itself. This ongoing quest for understanding propels science forward, reminding us that the universe's laws are not fixed, but may be gates that someday swing open to unimaginable realities. Each discovery challenges our perceptions, expanding our horizons and bringing us closer to understanding the true nature of the cosmos. As we continue exploring, the boundary between the possible and impossible blurs, revealing a universe more wondrous and enigmatic than ever imagined. 632 words. Current research into faster-than-light communication and travel is a wild frontier, full of tantalizing possibilities, but also riddled with fundamental obstacles rooted in the very fabric of our universe. For decades, the idea of breaking the light-speed barrier has been a staple of science fiction. Spaceships zipping across galaxies, or signals whispering faster than cosmic speed limits. Yet, when scientists look closely at what physics actually allows, the picture becomes more complicated and more fascinating. At the core of modern physics, as we've seen, is Einstein's theory of relativity, which declares that nothing with mass can accelerate to or beyond the speed of light. The energy required to reach light speed increases without bound as an object gets closer, effectively making it impossible for any object with mass to surpass that speed. It acts like an unbreakable speed limit, safeguarding causality, the cause and effect order of the universe, ensuring that no information or influence can travel faster than light. This principle is woven into the very structure of spacetime, the four-dimensional fabric that combines space and time. However, the concept of faster-than-light (FTL) phenomena doesn't automatically vanish into obscurity. Researchers have been exploring theoretical constructs like wormholes, hypothetical tunnels in spacetime that connect distant regions, in hopes they might serve as cosmic shortcuts. Think of a wormhole as a cosmic tunnel. If it could be stabilized and safely traversed, it might allow travel between points separated by light years in a blink, skirting the need for superluminal speeds. The catch is that creating or maintaining a wormhole might require exotic matter, substances with negative energy density, which so far is entirely speculative and hasn't been observed. Some physicists argue that even if wormholes could exist, traversing or signaling through them would still be complicated by causality issues, potentially resulting in paradoxes like time travel contradictions. These issues push the boundaries of our understanding and challenge the conventional notions of cause and effect. Meanwhile, quantum mechanics introduces phenomena that seem to transcend classical limits, especially through entanglement. Entangled particles share a connection so tight that measuring one instantly affects the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, suggests some form of instant correlation. But here's the key. Quantum entanglement cannot transmit usable information faster than light. It's more like a mysterious link that doesn't allow for communication that breaks the light speed cap. So, quantum weirdness, while defying classical intuition, doesn't offer a loophole for FTL communication. Physicists have also examined concepts like the Alcubierre drive, a speculative idea inspired by general relativity, where a spacecraft could be enveloped by a space bubble that contracts spacetime in front of it and expands behind. This would allow the craft to effectively ride a wave of spacetime distortions at speeds faster than light, but without actually moving through spacetime faster than light in its local frame. The problem? Like wormholes, it demands exotic energy, and whether such an energy source can exist remains uncertain. There is ongoing research into whether quantum fields, when manipulated creatively, could enable some form of superluminal signaling under very specific, highly theoretical conditions. But the consensus among physicists remains cautious. The fundamental structure of relativity and causality seems robust, and any violation of the light speed limit would require new physics, an entirely different framework that we haven't discovered yet. Interestingly, some hypotheses entertain the possibility that subtle, yet undetected aspects of spacetime might permit minute, controlled violations of light speed constraints, perhaps in relation to quantum gravity or string theory. But these are highly speculative, often mathematically complex, and lack experimental evidence. For now, practical faster-than-light communication or travel remains in the realm of theory, imagination, and science fiction. As we push the edges of understanding, what becomes clear is that our universe is remarkably resilient in upholding the cosmic speed limit. The more we learn, the more we see that the universe's rules, while perhaps poppable or bent in extraordinary ways, stick around in the end. They were built deep into the structure of reality itself, acting as guardian pillars that prevent certain phenomena, like FTL signaling or travel, from tipping over the cosmic order. But that doesn't diminish the allure. As scientists continue probing, every new insight could bring surprises, revealing novel pathways that challenge our current understanding. Yet, despite all this, the dream persists. Humanity's curiosity, combined with technological ingenuity, keeps the hope alive that someday we might find methods of interstellar communication or travel that seem to pierce these cosmic fences, methods that coexist with the universe's fundamental laws, or perhaps uncover entirely new laws of physics. Until then, speed limits remain limits, but the fascination with breaking them pushes us to explore, imagine, and expand the horizon of what is possible. From the mysteries of quantum entanglement to the speculative distortions of spacetime, the quest to go beyond light speed is less about immediate solutions and more about expanding our understanding of the universe itself, an adventure that continues to challenge, inspire, and mesmerize. The universe is expanding, one of modern cosmology's most remarkable discoveries. When discussing the speed of light, we often think of it as a universal speed limit for objects moving through space. However, in an expanding universe, the concept of speed is more complicated. It challenges our intuition and forces us to rethink what it means for something to move faster than light. Imagine spacetime itself stretching, carrying galaxies along. This is cosmic expansion. Instead of a spaceship racing through calm waters, galaxies are like raisins in a loaf of bread, rising and expanding. As the bread rises, the raisins aren't moving through the dough but are being carried apart by the expanding bread. Similarly, distant galaxies can recede from us faster than light, but it's crucial to distinguish their velocities through space from the expansion of space itself. Early cosmologists discovered that the farther a galaxy, the faster it appears to recede. Hubble's law states that recession velocity is proportional to distance. For galaxies a billion light-years away, the recession speed could be multiple times the speed of light, not because they travel faster than light through space, but because space itself is expanding. This superluminal recession doesn't violate Einstein's speed limit, because it applies to the expansion of space, not objects moving through space. This has profound implications. On cosmic scales, regions of space can drift apart faster than light, making it impossible for light from those regions to reach us. Light from galaxies receding faster than light will never arrive, placing them beyond our observational horizon, yet their influence persists subtly, as spacetime shapes the paths of light and matter, in ways scientists are only beginning to understand. Consider cosmic horizons, similar to Earth's horizon, limiting what we see. The observable universe is bounded by a cosmic horizon, beyond which light hasn't reached us since the Big Bang. As space expands, this horizon also stretches, revealing a universe much larger than current views. Objects whose light started travelling toward us billions of years ago are now unreachable, because the expanding space between us and them grows faster than light can bridge. What does this imply about the speed of light? It shows that while the speed of light is a fundamental limit in local physics, defining how fast signals and particles can move within small regions, it doesn't set an absolute boundary on the universe's large-scale behaviour. Cosmic expansion introduces a loophole. Space-time can stretch faster than light, isolating regions not because they move faster than light locally, but because space itself expands faster than light can travel. This understanding underscores that space-time is a dynamic, malleable entity. It's not just a passive stage, but an active influence on what can happen in the universe. When we say, nothing can travel faster than light, we refer to local velocities, how fast things move relative to their surroundings. But at the cosmic scale, expansion is a background process that can outrun light, changing our understanding of cosmic speed limits. In the early universe, phenomena like inflation and extremely rapid expansion show that the speed limit has a nuanced role. During inflation, space expanded exponentially, surpassing the speed of light globally. This period set the foundation for the universe we observe today. The universe was stretching faster than anything could travel across, leading to the large, uniform cosmos we see now. The influence of cosmic expansion fundamentally reshapes our understanding of the speed of light. Our familiar constant, cs, per local travel, is part of a bigger, more complex picture. When spacetime can change, stretch, and grow, the lines between speed and limit blur. It's less a static arena of objects racing through space, and more a vibrant universe where the fabric of reality influences the limits we trust. This dance of spacetime and light teaches us that speed limits depend on context. The speed of light remains central, but cosmic expansion transforms it into a cosmic storyteller, one that challenges our understanding and pushes physics beyond traditional boundaries. It invites us to see the universe as a dynamic entity, where the fabric of spacetime shapes the limits, not just objects within it. In this cosmic context, the universe reveals that speed limits are not absolute but environment-dependent. The speed of light is a fundamental constant in local physics, but on the grand, evolving scale of the cosmos, the fabric of spacetime itself can stretch faster than this limit. This underscores the universe's complexity beyond our intuitive notions. Cosmic expansion affects our understanding of the speed of light by emphasizing that local laws of physics do not always determine large-scale structure. The universe's expansion acts as a background process capable of outrunning light, creating regions of space forever beyond our observational reach. This, more than individual velocities, sets the ultimate limit on what we can observe and influence. This perspective adds depth to Einstein's theory, showing that the universe is not static but evolving. While local velocities are bound by the speed of light, the expansion of space can surpass this limit without contradiction. This complicates but enriches our understanding of the universe's structure and the fundamental nature of physics. In conclusion, cosmic expansion significantly modifies how we think about the speed of light. It shows that the universe's growth can outpace light, creating a cosmic boundary that defines what we can observe. While the speed of light remains a core principle governing local interactions, the universe's dynamism demonstrates that the limits of speed are more flexible and context-dependent than previously thought. A light cone visualizes how information and causality propagate through spacetime. Imagine standing in a dark field at dusk. The horizon marks where sunlight meets night. Similarly, in spacetime, an event emits light in all directions, creating expanding spheres called light cones. These cones are fundamental for understanding the universe's operation on cosmic and quantum scales. A light cone isn't just about light. It maps causality, the principle that cause precedes effect. Think of an invisible bubble expanding from an event point, representing all the locations in space and moments in time that light could reach or be influenced by that event. These cones depict past and future, showing what we can observe, what influences us, and what remains forever unreachable. There are two key parts: the past light cone and the future light cone. The past cone includes everything that could have sent signals or influence to the event: galaxies, stars, photons traveling across the universe. The future cone contains all possible effects that could arise from the event. It's where causal influence extends forward, dictating what can be affected or changed. This boundary isn't arbitrary. It's embedded in the fabric of spacetime described by Einstein's relativity. Because nothing can travel faster than light, these cones set the ultimate limits of information transfer. No signal or influence can leap outside a cone. Anything beyond remains causally disconnected regardless of technological advances. In cosmology, light cones offer a framework to understand the universe's structure and history. When the universe was born in the Big Bang, the initial singularity emitted a flood of light, filling space with an expanding light cone, known as the cosmic microwave background, CMB. Its shape and evolution trace cosmic history, revealing how regions of space connected or separated over billions of years. Cosmologists use light cones to determine observable parts of the universe and how cosmic expansion impacts our view. As space expands, distant galaxies recede faster, and their light takes longer to reach us. Some regions slip beyond our cosmic horizon, the boundary of our observable universe. The shape of the light cone defines this boundary, separating what is knowable from what's forever out of reach. The concept becomes vital during cosmic inflation, the rapid early expansion of space. Regions that were once close inside the same light cone were suddenly propelled apart faster than light. This explains why distant regions appear causally disconnected, yet exhibit remarkable uniformity, as inflation caused them to have shared properties early on. Light cones also clarify phenomena like black holes. Inside the event horizon, light cones tilt inward sharply, signaling all paths lead inward toward the singularity. From outside, objects crossing this boundary cannot escape. The structure of light cones dynamically shapes what can influence or be influenced, emphasizing gravity's role in spacetime. On a deeper level, light cones deepen our understanding of spacetime, which merges space and time into a single fabric where causality is woven into every thread. They serve as landmarks, delimit boundaries between what is possible and impossible, known and unknowable, shaping our view of cosmic architecture. By charting these invisible, expanding bubbles of influence, physicists interpret the universe's story, from its fiery beginnings to its expanding future. Light cones show that influence travels at the speed of light, establishing boundaries to our reach. Beyond them, influence ceases, making regions causally disconnected. Within them, a complex web of interconnectedness, causality, and wonder exists. They help us understand why some parts of the universe are observable and others aren't. Light cones mark causally connected regions, and their shape evolves as the universe expands, causing distant regions to slip beyond our reach and forming horizons. These cones trace cosmic history, revealing how early connections formed and how expansion shaped what we see. In black holes, the tilt of the cones signals the influence of gravity. Inside the event horizon, cones tilt inward so completely that no paths lead outward. This illustrates how gravity influences spacetime's structure, shaping what can influence or be influenced, and creates regions of no return. Ultimately, light cones are essential because they connect causality, information flow, and the universe's large-scale structure. They visualize the limits and possibilities within spacetime, enabling scientists to understand cosmic history, horizons, and future evolution. They demonstrate that the universe is interconnected within boundaries set by the speed of light, forging order from chaos and revealing the cosmos's deepest secrets. Black holes and their event horizons exemplify how the universe enforces a fundamental speed limit set by light. Consider a star so dense that its gravity warps spacetime to the point where no light can escape once it crosses the event horizon. This boundary is the ultimate no-return surface where escape velocity equals the speed of light. The fabric of spacetime folds inward with such curvature that our usual understanding of motion is subverted at this boundary. The event horizon isn't just a surface, it's a manifestation of extreme spacetime warping. Normally objects can accelerate, decelerate, or stop, but beyond the horizon, these notions break down. Physics laws still hold but operate differently under intense curvature. Here, the concept of speed takes on a different meaning. Objects appear to slow dramatically to outside observers. Light and information are affected by gravity, causing infalling objects to seem frozen in time at the horizon, demonstrating how gravity and spacetime geometry intertwine with motion. Black holes teach us that space and time are flexible, woven into a single fabric called spacetime. The event horizon enforces the speed limit. Nothing inside can escape unless it exceeds the speed of light, which is impossible by physical law. Importantly, the horizon isn't a physical surface but a mathematical boundary, where spacetime becomes so warped that escape requires surpassing the speed of light. No amount of energy can enable escape, making the horizon a point of no return. General relativity frames gravity as a manifestation of spacetime curvature. When mass compresses into a black hole, the curvature intensifies dramatically at the horizon. This boundary marks the maximum limits of speed and motion. To escape, one would need to travel faster than light, an impossible feat, sealing the black hole's definitive boundary. Faster-than-light phenomena, like wormholes or warp drives, suggest ways to bypass the cosmic speed limit. Wormholes are hypothetical tunnels connecting distant parts of spacetime, shortcuts. While they might allow apparent superluminal travel from an outside perspective, locally, travel through a wormhole remains limited by the speed of light. No object moves faster than light within it. Similarly, warp drives involve manipulating spacetime, expanding behind and contracting in front to simulate faster travel. This relies on exotic matter and negative energy, concepts still theoretical. Crucially, spacetime bending and stretching don't violate the speed limit because local motion remains subliminal. The superluminal effects are a geometric illusion, not actual faster-than-light travel. Quantum entanglement complicates the picture further. Particles can share correlations instantaneously across vast distances, yet no usable information travels faster than light. This spooky action at a distance confirms the speed of light as a universal cap for information transfer, reinforcing its fundamental role in the cosmos. Black holes and their horizons demonstrate that the universe enforces the speed limit with strict authority. When spacetime warps so severely that escape becomes impossible, and information cannot outrun the boundary, a profound truth emerges. The speed of light is an insurmountable barrier. Despite speculative ideas of exotic travel or science fiction, the cosmic speed limit remains absolute, maintaining causality and the order of cause and effect. It's a fundamental feature woven into the fabric of reality, ensuring that no information or matter can travel faster than this universal limit. This boundary prevents violations of causality, meaning effects cannot precede causes, and preserves the universe's chronological order. While general relativity allows for constructs like wormholes or warp drives, these don't truly bypass the speed limit. They manipulate spacetime's geometry, rather than breaking the light barrier. Actual local velocities always stay at or below the speed of light, ensuring the universe's consistency. In essence, black holes and their event horizons illustrate that the universe is governed by strict speed restrictions. These boundaries enforce limitations on escape, information transfer, and motion, reinforcing the principle that nothing may surpass the speed of light locally. Such limits uphold the laws of physics, causality, and the structure of spacetime itself, highlighting the universe's consistency amid its complexity and the tantalizing possibilities of advanced theories. Despite the allure of faster-than-light travel, the ultimate cosmic rule remains inviolable. The speed of light is the universal speed limit, embedded into the very foundation of reality. Imagine standing in a vast, empty field, watching the horizon stretch farther and farther away. It's beautiful, mesmerizing, and daunting all at once. Now, what if that horizon suddenly begins to expand faster than the speed of light? It sounds impossible, doesn't it? Because we've been told that nothing can travel faster than light, that this speed limit is woven into the fabric of the universe. But here's the twist. While objects with mass cannot reach or surpass light speed within space, the universe itself can do something even more extraordinary. It can expand faster than light. This idea is at the heart of what cosmologists call cosmic inflation, the rapid, exponential expansion of space just fractions of a second after the Big Bang. During that moment, the entire universe ballooned outward at a rate far exceeding the speed of light. The key is that no object within the universe was moving through space faster than light. Instead, the space between objects increased, stretching at a superluminal rate. This is a subtle but crucial distinction. Space itself is stretching. What does that mean for us? It changes our understanding of cosmic speed limits. When we say nothing can go faster than light, it's about objects moving through space, not space itself expanding. Think of a loaf of raisin bread baking in the oven. The raisins are like galaxies, embedded in the dough, the universe. As the bread bakes, the dough expands and the raisins move away from each other. They aren't rushing through the dough to get distant. The dough is growing. No rules are broken because the raisins aren't exceeding any speed limit. They're just carried along by the expansion of the bread. In the early universe, during inflation, space expanded at an incredible rate. This rapid expansion caused regions of space to become causally disconnected, meaning light had no chance to bridge the growing gaps. That's why the universe appears so uniform on large scales. The parts now far apart were once close enough to influence each other, but inflation tore them apart faster than light could travel. This explains the universe's large-scale uniformity. What does this mean for the galaxies we see today? It means some galaxies are moving away from us faster than light, not because they're travelling through space at superluminal speeds, but because space itself is stretching. The light these galaxies emit now may never reach us because the space between us is expanding faster than the light can travel. That's why, in the distant universe, galaxies appear to recede faster than light. The universe's expansion exceeds light speed, but the laws remain intact. They govern objects moving through space, not the expansion of space itself. This expansion has deep implications for the observable universe, the part we can see or might see. Due to this accelerated expansion, there's a horizon beyond which we can never observe or influence. Light from galaxies beyond that horizon will never reach us. They're effectively cut off, their light lost in the expanding darkness. Over time, more regions slip beyond this cosmic horizon, making our observable universe smaller even as the universe continues to grow. This faster-than-light expansion isn't just a curiosity, but a fundamental part of the universe's history and future. It can happen without violating the cosmic speed limit because that limit applies only to objects moving through space, not to the expansion of space itself. The universe's fabric stretching faster than light isn't about movement in the traditional sense, but about the geometry of space-time transforming, a cosmic dance governed by general relativity. This makes the universe mind-bending. Its true nature defies simple notions of speed, motion, and boundaries. Instead, it's a vast, ever-expanding canvas where understanding requires thinking beyond objects and velocities. Sometimes, the only way to grasp what's happening is to embrace the dynamic, stretching fabric of space itself. That's the key behind the universe's expansion. Faster than light, but in harmony with the laws we know, these laws continue to inspire awe and hunger for further understanding. 588 words. Richard Feynman's insights have revolutionized how we see the universe's very fabric, peeling back layers of mystery to reveal the underlying rules that govern everything from the tiniest particles to the vast cosmic expanse. At the heart of his legacy is the elegant simplicity of the Feynman diagrams, a tool that turns complex quantum interactions into visual stories, making the impossible seem almost straightforward. These diagrams weren't just clever illustrations, they provided a new language, one that exposed the intricate dance of particles and forces at a level previously thought inaccessible. What Feynman uncovered fundamentally reshaped our understanding of the limits within which our universe operates. He showed us that at the subatomic scale, what appears random and chaotic is, in fact, governed by probabilities, intrinsic uncertainties woven into the fabric of reality. This realization challenged classical notions of